starting in 10 minutes. We'll be starting in 5 minutes. Introducing George Saab.
Hey, good morning. Thank you for joining us. I want to thank everyone who's here in the room who braved the elements to be with us today. They actually had a survey for the most popular way to get here today. Anyone know what it was? Backstroke. All right, so in addition to everyone in the room, I'd also like to extend a warm welcome to the thousands of people who are joining us online. And thank you for joining. This is the Oracle DevLive Level Up Java Day. And we've got a great program for you. In addition to this session, we're going to have 3 tracks that are going on all day, also streaming online. So there's a lot to look forward to. So really, really happy to be with you today. We're gonna launch JDK 20 in just a minute, but first, just wanted to reflect a little bit on where we are and how far we've come. So we're now into the 28th year of innovation on Java technology. It's amazing to be here. We've got a lot of people on the team who've been here all the way through, working on bringing you a great platform. Such a great platform, in fact, that many enterprises out there really rely on Java to run their business. I think of sort of the number of things that I do throughout the day and the number of those that are impacted or sort of touched by Java in some way, and you just lose count. It's just astounding. What's interesting about this is that, a few years ago, we took a step back and said, where do we want to take things? And one of the things that was very clear to us was that we wanted Java to be a platform that continued to evolve and help solve the business problems that people out there are facing every day. And so one of the things we did was made a change to how we deliver it. We're going to talk about that a little bit. But the result has been that we have a continuous pipeline of innovation. And the feeling of the people on the team, and I think what we hear from people who are using Java, is that pipeline of innovation has never been richer than it is today. So we're going to talk a little bit about how that's going. We're going to talk a little bit about Java 20 and also give a little bit of insight into some of the things you can hear about throughout the rest of the day. What's been one of the sort of some of the most important things that have made Java so popular? Well, I think there's been a constant dedication to performance, stability, security, and also compatibility and maintainability. These are all things that sort of permeate everything we do when we're thinking about improvements to Java. And it sometimes means that we're a little bit conservative. If we're not sure how something needs to be done yet, or we think it's going to impact one of these things in a negative way, we may hold off until we can figure out the Java way of adding it in. I think the numbers kind of speak for themselves, and there are a lot of things that have helped make this the case, right? Why is Java the #1 language? Well, it's because people can trust Java. They can trust Java. They can see what's going on. They can take part in the development. We don't do a bunch of work, behind closed doors and throw it over the wall. Instead, all the development that we're doing is done in projects mostly led by Oracle in the OpenJDK community. And you can go to OpenJDK, you can join the mailing lists, you can see what's happening. You can witness the design discussions by experts and really understand what is motivating adding this particular thing to Java. Why was it done this way and not some other way that might have seemed more obvious? And I think that's something that's pretty unique, and we hear from developers time and time again that they really love the ability to get that kind of insight, not only into what's in Java today and how did it get there, but also where is it headed out into the future. I think a result of that, again, has been we've added this 6-month cadence that basically makes it so you have a very, very predictable set of releases coming out. Gone are the days when a release would be worked on for 2 or 3, maybe 4 or 5 years, and you really wouldn't know when it was going to be done. Instead, developers and enterprises can know that there's going to be a release. Now, they might not know exactly what's going to be in it until we get into the development cycle, but there again, we've worked to reduce surprises. And one of the ways that we've done that is taken advantage of these 6-month releases in order to introduce features as previews. And so basically what that means is it's a fully production-ready, finished feature that's added into a release but hidden behind a flag. Now, you might say, well, why is it hidden by a flag? In the old days, in that form, it would have gone into Java, and that would have meant that we poured the concrete on the API, and it isn't going to change ever, even if there were sort of problems with it. And so with the 6-month cadence, what we're able to do is put it in as a preview. That means that if I turn it on, I can try it out. This means a lot more people are trying these features out and giving us feedback before that concrete is poured. The result of that, of course, is that we can make small changes. We can make tweaks here and there and make the APIs as solid and as intuitive and as consistent as they can be. And this has been really, really useful. So what that has led to then is also this sort of blooming of innovation in the Java platform. In the old days with the release, every few years, if something was almost done, you really kind of want to get it in, and there's so much going into one release that once it's done, wow, what are we doing next? I don't know. I guess we better go back to the drawing board. Instead now, with these releases happening all the time, it's easier for smaller increments of change to be broken off and delivered into successive 6-month releases. And so basically that's meant that there's always something going on. One release might have features from one project, another one will have from a different project, and so there's never this sort of need to completely restart. And this is very important because when we think of evolution for Java, one of the things that we want to do is make sure that we're adding this innovation, but we're not breaking you. We're basically making it so this pipeline of innovation can be taken advantage of by existing applications moving forward. But that innovation is there in order to help solve new problems that come about. Right? We want the investment that you as a Java developer have made in choosing your programming technology to basically for you to be able to get some kind of return on that. And so what this means is that as new programming paradigms come along, as new hardware comes along, as the world changes and the tools that you have need to change with it, that can be done in a way that is graceful. Here again, we try to have this balance between being conservative about putting new things in, making sure that it's actually something that's going to stand the test of time, but then also not being too conservative, making sure we are continuing to move the platform forward. So how do we do that? Well, I mentioned OpenJDK community earlier. This is where we do the development. These are some of the projects, just a small number of the ones that are going on right now in OpenJDK, stewarded by folks on my team at Oracle. And I think if you look at this, you'll see there's a very rich set of projects that we have. We have things like Amber, which is working on the Java language and making small improvements to it over time. And Amber has actually delivered into every 6-month release that we've had. We have Loom, which is working on improving scalability of Java, the already great scalability and taking it to the next level. We have Panama, which is about integration of Java with native libraries in both directions. We have things like ZGC, which is really the state of the art for garbage collection, and making it so you can have really predictable and low latency for even massively large heaps. We have things like Valhalla, which is just getting to the point where we're going to start to see deliveries from it coming forward. And this is about rethinking the way that memory management is worked, or the memory model for Java is worked, so that we can really take advantage of hardware that exists today and going forward that really nobody had thought of when Java was originally created. And finally, we have something like Leiden, which is just getting started now, looking at how we can take all the great work that's been done and investigation into different ways of improving startup and warm up for Java applications, and bring that into the Java specification in a way that feels natural and makes sense. Okay, so I mentioned things coming in from those projects and the 6-month releases. Well, of course, when we made this change, as you can see here, from the old major releases in Java 8 and 9 to the 6-month releases, we didn't magically find a way of doing 3 years of work in 6 months. Instead, what we did was thought about how we could break down the problems we were trying to solve into smaller problems that had smaller increments of solution coming in. And so what that has meant is that each of these 6-month releases actually has a smaller increment of change, but made to you available to you as a developer more quickly. And so developers, I think originally there was sort of a, gosh, I don't know, how's this going to work? Are these betas? Are production ready? What are they? And I think now that we've been doing this for over 5 years, over 10 releases, people have started to get that, wow, these are production ready, right? The only thing is they're production ready, but I need to understand that things that are preview might change. And if I want something to run in production and not need to move forward to the next release, then I should probably be looking at a support offering from a vendor like Oracle or one of the other choices that I have in the Java industry in order to be able to get a long-term support stream of updates. And so that basically means that I've got a particular release, it's in production, I just want to get fixes for performance, stability, and security, and not necessarily have to have new features coming in. And so the nice thing about this balance is it means that there's really a choice for lots of different needs. Before, what we really had with the major releases was we only effectively had things like long-term support releases. Now we also have the 6-month releases bringing things to developers in production-ready format on a very, very frequent basis. Speaking of long-term support releases, I did want to mention when 17 came out, we talked about the idea that we were starting to hear from people that they like these, but they'd really like to see them happen more frequently. And so I am very happy to say that the next release for which Oracle has planned to offer long-term support will be JDK 21 in September of this year. Okay. So with that, I am very happy to announce that Java 20 is available. Some of you may have already downloaded it. Many of you may have already downloaded some of the early access builds and given us feedback. We'd like to thank you for that. But basically, you can now download it and go ahead and use it. And please pay attention to the 7 JDK enhancement proposals. These are basically JEPs calling out larger features. And all of these are things that have come in from Project Amber, Panama, and Loom. But the changes in 20 are not restricted to just those 7 JEPs. There are thousands of fixes for performance, stability, and security, and even smaller enhancements. And so there are going to be sessions today where you can learn more about all of the content of both those 7 JEPs, but also many of the other changes that have come in. So I would encourage you to attend those and learn about them. We also have the availability of Java FX 20. So nice to see that moving along with client and graphical technology. Really, really just a great release, and I think a nice step forward from 19. So with that, I'd like to thank all of the folks that helped bring this about. Of course, working on this technology in the OpenJDK community, we try to be very welcoming to more parties, and we'd like to thank those parties for the contributions they've made. Here, really interestingly, we see a lot of contributions from different parties around the industry that have an interest in making sure that Java support is really strong for their operating system or their hardware or their technology stack. Or their cloud. And so that's really nice to see. We're proud of the growing set of contributors that we have. Interestingly, for Java 20, the sort of second to largest contributor was independent. And so that actually means folks who have come along that are not necessarily affiliated with some other company, but that maybe from academia or some other place that are making contributions. So really nice to see that as well. I think it's a testament to the spirit of open source. Here, of course, the largest contributor by far still remains Oracle. Basically larger than all the others combined. And that's something that is a burden we're happy to bear. We're happy to shoulder that responsibility because we think it also gives us an opportunity to focus on and provide some stewardship and direction for the technology. And that's mostly what we see. Most of the projects that Oracle are contributing to here are really ones that are about the evolution of the platform, the language, the VM. And so we think that the fact that we're doing that extent of contribution is also one of the reasons why people are increasingly turning to Oracle for their needs to get updates and support and value-added features. There are, in addition to the technology itself, quite a lot of challenges that people face in trying to adopt technology and maintain it and use it to run their business. And so that's really what the Java SE subscription is about, is helping those customers with those challenges. And what we've seen here is with the Java SE universal subscription, we include not only support and updates, we also have a wealth of tools and value-added features. Everything from the Java Management Service, which I'll mention in a moment, to things like the Java SE subscription Enterprise Performance Pack that lets people who are running something on Java 8 get even much better performance up to the level of Java 17 as a drop-in replacement. We have things like Graal VM Enterprise and the great features that that brings along. And we also have turned more and more, we've heard from our customers that people don't want support just for the JDK. What they want is support for their entire stack and everything that they run in Java. And so this is something that we've added basically to help you with whatever your problem and challenge is when you're running something in Java. Okay, so with that, really happy to see the sort of adoption by customers. This is both new customers, and we have over 10,000 subscribers. We also, that represents over 50% of the Fortune 500, and we've got a really high renewal rate there. This is something that is basically all over the planet, and we're quite happy to see it and hear the satisfaction from our existing customers. In order to help people, again, with how they're using Java in their enterprise, we have something called the Java Management Service. And so this is an Oracle Cloud Native service, which you can use in order to keep track of where am I running Java, what versions is it running, what applications is it running, and basically handle the management and installation of updates there. This is something that was originally launched in June of 2021 and is available now in 35 OCI regions around the world. So wherever you are, there's probably an instance that's running somewhere close to you. With that, we also announced that the JMS Discovery services are available to everyone, whether you're a subscriber or not. So this is something that you can use just to keep track of that. Where am I running Java? What is it running? What kinds of applications? And then in addition to that, if you are a subscriber, there are a lot of advanced services that you get. Things like understanding your usage of crypto, understanding third-party library use, and keeping track of, am I above the security baseline on that? Are there things that are coming along in the crypto roadmap that may affect me? Here again, there's a great session that's going on later today that will talk a lot about this, and you can ask all kinds of questions. So please attend that. Okay, so with that, we think that Java is not just about technology. It's always been about a rich community and a rich ecosystem. And so this is something that, as we've gone along, Oracle has tried to play its part in encouraging this growth and this momentum. And we do that in a lot of different places. Basically, in working with the Java community process, I mentioned the OpenJDK community, but also programs like the Java Champions, the Java user groups, things like the Java Magazine, JDuchess, the Oracle Academy and University for training at different levels of education. These are things that really help make and keep the Java ecosystem strong. And in fact, I get asked from time to time, where's the best place to go and learn about things and what's happening? And so here, I'd really like to refer everyone to dev.java and Inside Java. So dev.java is basically a site for developers for Java. So you can go and find out what's happening and learn about Java, check it out. There's a great set of resources available there. Inside Java is basically like an RSS feed of a lot of the information that has been produced and things that have been published, primarily and first from people from my group, but I think we're going to see that pool expanding over time. So this is basically a great place to go and read in-depth articles by the people who brought you Java about what they're doing, what they're interested in, the problems they're trying to solve, etc. So check those out. And finally, I just wanted to mention the awesome developer relations team that we have. These are folks that you're probably going to see at conferences that you go around the world to. And you'll see some of them actually here in the conference center today. Really, really pleased to have these folks. In addition to seeing them in person, you can see them online. So when you go and look at social media about Java, or you look at our Java YouTube channel, these are the folks who are producing a lot of the content that you see there. So please check those things out. We love to hear your feedback, and I think you'll really enjoy it. Another area that I wanted to call out just in very specifically, newest member of the team, Heather Stevens, who has joined us to focus on Java in education. This is something we think is critically important because we've got a lot of people out there who know Java. We have generations who are coming along for whom, gosh, what is this technology? I've never heard about it. It's not like the latest, coolest, newest thing. But what we're seeing is increasingly that new generation are finding Java, and they're finding out about what's there, and they're learning about the way that it helps them solve the challenges that they have today, and increasingly the challenges that they have going forward. So all of these things, you're going to hear more about during the day. Thank you so much for coming along. Thank you to all of the people who have joined us online, and I hope you enjoy the show.
We'll be starting in 10 minutes. We'll be starting in 5 minutes. We'll be starting in 1 minute. Introducing Aurelio Garcia-Ribeyro.
Good morning, and thank you for those of you that joined us in person. It's been a while since I've had people in the room, so bear with me. Today I'm going to talk about what's new in JDK 20. Now that we have a feature release every 6 months, part of my job is to go about and tell you about the JEPs and what has been added. So I'll read all of the JEPs and condense them so that you don't have to read them. You can just hear this session and then decide which ones you want to learn more about. We will cover the ones that just came out this morning in JDK 20. So JDK 20 is the first release of 2023, and it's the last release prior to the upcoming next long-term support version. JDK 20 replaces JDK 19 and will in turn be superseded by JDK 21 later this year in September. And JDK 20, as you can see here by the light color, is offered under the no-fee terms and conditions, so everyone can use it in production at no cost. We have 7 JEPs, all of which are either incubator JEPs or preview JEPs. Now, most library improvements start as incubators. Once they're mature enough, they might be added to the standard, or in some cases, they may move on to previews. Preview mode is a step closer to being added to the standard. Features in preview are already fully specified, and they're completely implemented and tested, so they're good, but they are impermanent, so they might change in the next release. Previews are the usual way to test language features and JVM enhancements, because those cannot be constrained to an incubator module. And using a preview feature requires that you accept that the code might not work exactly as is in the next release. So to ensure that you know that you're doing that, when you're compiling code with preview features, you're going to have to pass a flag and let it know, yes, I know what I'm doing. And in order to avoid somebody sneaking a preview feature into a library that you use, you also have to pass a flag at runtime. Now, we've grouped the JEPs on this release into 3 parts. The language features, which come from Project Amber. We have library improvements, and they come from Project Panama, these 2. And we have 3 improvements that are from Project Loom, which aim to update how Java manages concurrency. So let's dive right into those. We always start with the language features because these are the ones that are most likely to impact the largest number of developers, and they're also the most fun to showcase. JDK 20 brings back a second preview for record patterns, which makes it much easier to deconstruct records and operate on their components. Record patterns can be nested to access data at any level of the record hierarchy. So let's take an example. Before we go, though, let's review the 2 changes that made this possible. JDK 16 introduced pattern matching to the instance of operator. So prior to this change, if we wanted to do something with an object, if it was a certain type, we'd have to do a test. Then we have to declare a variable, then manually cast it, and then we can use it. With pattern matching, we can do all of that in a single line. JDK 16 also brought in records, which simplified the creation of classes that are used just to simple carriers of immutable data. Records are more than just a way of typing a little bit less when you're declaring a class. Knowing that a class is a record will allow us to do some interesting optimizations, like the ones that we're going to have now with record patterns. So in JDK 20, we can see a combination of these 2 with pattern matching and record classes. In this example, we have defined a record class called point with the expected components x and y. Now, in this print_sum method, we want to first test if the object we received is a point, and if it is, we want to use the values of that point. Notice that intermediate variable p that has a different orangish color. We've only created it to access the x and y values. It would be better if we could not only test to see if it's a point, but also extract those values and let us use it directly. In other words, right, this is the new code, and the part that's highlighted, point, int x, int y, that's a record pattern. Now, the true power of pattern matching is that it scales elegantly to match more complicated object graphs. So let's consider the following declarations. Let's make the point a little bit more complicated, right? Let's introduce a color, and then we defined a color point as a point with a color, and we define a rectangle as 2 color points. Now, we can extract the components of an object with a record pattern. If we wanted to get the colors from the upper left, we could write something like this, right? And we have the upper left dot color. But again, you see here that I'm using the upper left only to access the color. If we can nest the record patterns, we could deconstruct that first color point into its components and access directly the parts that I need. What's more, I can use the var keyword so that I don't have to define the types. I can just infer them. And that makes it slightly easier to read, especially if I'm not going to use them. Now, the second preview, I mentioned this is the second preview of it. It has added support for record patterns to appear in the headers of enhanced for statements. In this example here, if we wanted to iterate over a group of points and do something with the components, we don't have to introduce that extra variable points and then read them. We can get the values directly. JDK 20 also brings us pattern matching on switch expressions and statements. Now, using this feature, we can test an expression against a number of different patterns. In the past, switch statements used to work only on a few types, like a numeric, an enum, and a string. In JDK 14, we introduced switch expressions and allowed other case labels. But you still couldn't switch to test an object against an expression to see if it belonged to a particular type. The best we could do at the time was a collection of chained if statements. Pattern matching for switch extends the case labels to include the patterns and null in the list of cases. So we can make this code dramatically simpler. Now, as a bonus, this is not just easier to read, but this is optimizable by the compiler. Now, the case statement has to be exhaustive, so in most cases, you do want to add a default value. And now that we can test for null inside the switch, you don't have to check for the variable's null case outside of it. Now, to maintain backward compatibility, if you only have a default label, it will not match null. But you could put null and default in the same case if you want to treat them the same way. Now, after a successful pattern match, it is often the case that we need to do some further tests, right? In this case, we have, okay, we want to do something with strings, but we want to do something special if the string is of length 1. Now, we can improve this if we can mix a combination of the pattern matching and the condition. So now we can put pattern matching and an extra condition, allowing with the when clause, right? So now in this case, the first case will match strings of length 1, and every other strings will be caught by the second case. Now, the when clause can use any pattern variables declared in the pattern in the case label. We have to be careful with the order of these expressions now. If we were to invert the order, then the case string s would catch every string, including the ones of length 1, and that would be an error. So that would be dominating, a pattern would dominate the second one. So doing so will result in a compile time exception. As before, the switch statements need to be exhaustive, so you may want to throw in a default value in there, unless you're enumerating on an enum or on a sealed class, and you are covering all the possible values in your statements. So those were the language features. Now, let's take a look at the changes in the library. Now, the Java libraries are one of the reasons why Java has become so popular. They handle most of the hardest jobs, like implementing cryptography algorithms or figuring out the logic for multi-threading when you want to sort some collection. They also handle all of the tasks that are common that most developers want to do, and they're kind of tedious, and it'd be hard to get them all right all the time. JDK 20 brings us one preview and one incubator, both of them from Project Panama, which aims to make it possible to interoperate between Java code and foreign code. And when we say foreign, we mean anything that's not Java. The first JEP is a second preview of the foreign function and memory APIs. Now, the goal of this feature is to make it simple for Java programs to use functions written in languages other than Java, initially in C, and to safely access memory that is not under the control of the JVM. We already have the Java native interface, JNI, to access non-Java code. But it's very cumbersome, and it requires code to be maintained in C on top of Java. So this replacement that we're working on should have the performance as good as or as better than the current alternatives. And what are the alternatives? Historically, you have one of two ways to access foreign memory. There is the supported way, which uses byte buffer. And there is the hacky way using SAN, MISC, and SAFE. Byte buffer is limited to 2 gigabyte size regions. Now, this used to be large enough, but it really nowadays isn't. So you probably have some systems where you may need to access more than 2 gigabytes. And there's also the problem that if you use byte buffer, you can't really tell the JVM when to deallocate the memory. You'll just be subject to whenever the garbage collector goes through it, it'll catch it, and then it'll do it. So if you don't like those two constraints, you could use SAN, MISC, and SAFE. It's an internal JDK API, which gives you all the control you could possibly want, and probably a lot more than what you wanted. As the name implies, it is unsafe. So you're using a non-standard API, which means it's not guaranteed to remain the same in some future version of the platform, not even on an update of that release, though we haven't changed it in many years, and we have no intentions to do so yet. Right? You also won't get any help from the platform in deallocating memory. So if you get it wrong, and it's quite easy to get it wrong, you can have some unexpected errors that you normally wouldn't see on a Java application, including not just the JVM crashing, but also some silent memory corruption. So not really good choices here. Right? Now, for accessing foreign functions, that is for running a library that is not written in Java, we currently only have JNI. Right? And it's possible to do it, but it's very clunky. So in order to use JNI, you'll have to maintain a Java API, a C header file, and a C implementation that will actually call the library. And that means that, unlike the rest of your Java code, you will have to use different tool chains for each platform, because you need different tool chains for C in each one of the platforms that you support. And you want to have to keep those artifacts in sync with the Java library. Right? With the non-Java library. Now, if that non-Java library is moving quickly, this can become a lot of work. You also have to deal with the difference between Java, the Java type, and the C type systems. Right? Java uses objects, C uses struct, and you have to unpack that using native code. Some developers choose to simplify this by flattening their objects, or worse, you can go back to SAN, MISC, and SAFE and start moving addresses around, and you're back in unsafe mode. So the new foreign function and memory API offers classes and interfaces that will allow you to allocate foreign memory, manipulate and access that foreign memory, control the timing of that allocation, the allocation, call foreign functions, and let's take a look at that. How will that look like? So you don't have to really go through the whole code. I'm just going to quickly point some details here. Let's say we want to sort some string, and we have a C library that has a function called radix sort. First thing, we need to get a handle for that. So we use the linker and symbol lookup and a couple of lines of just Java code, and there we go. We have now a handle to the library. The second step is to put our variables in some location in memory, or in the heap. So we create some variables, some strings to put them in there. Step 3, we need to properly manage off-heap memory. We do this by using the try with resources. So we're sure now that regardless of what happens, the memory is going to be freed as soon as it's no longer needed, whether there's an error or not. So that makes it much simpler. Step 4, we need to create an off-heap place to put all of our variables. Step 5, and we have to iterate and copy our variables into off-heap. You see now, this may look a little complicated, but if you've written JNI code, this is very simple, right? Step 6, we're using the handles to call our library, and then we copy the memory from off-heap back to on-heap. Now, what's marked here as step 8, that's handled for you by the JVM, right? So we'll take care of all the memory, and it'll happen as soon as you go through that line of code, error or no error. Now, if you have written any JNI code, this should look dramatically simpler. And if you haven't written any JNI code, with any luck on these APIs, you probably never will have to. The second API improvement is in a 5th incubator, and I think that's a record. That's the longest incubators we've had so far. This is the vector API. Now, vector computations allow systems to execute operations on vectors instead of applying the same operation to several values one at a time. And this can result in significant performance improvements. Hotspot already supports auto-vectorization, so it sometimes can detect when a scalar operation can be transformed to superword operations and mapped to vector instructions. The problem is that the set of operations is very limited, and it's fragile to the changes in the code shape. So with this API, it will be possible to write very complex vector algorithms in Java in a way that will be predictable and robust. Vector APIs under the hood use some of the foreign functions and memory APIs that I just talked about, which are already mature enough that we feel comfortable creating this dependency. Here is a conceptual model of a vector operation. Instead of needing to repeat an operation multiple times, we can achieve the same result with a single pass. All right? Pretty straightforward. Now, the goals of the vector API are to create APIs that are clear and concise. So you should be able to create a wide range of vector computations consisting of a sequence of vector operations with loops and possible control flow. It has to be platform agnostic, so it should be CPU architecture agnostic. And as usual in Java APIs, when there is some platform optimization or portability conflicts, we will bias towards portability. We want reliable runtime and performance. That means that on capable x64 and ARCH64 architectures, the Java runtime will compile vector operations to corresponding efficient and performant instructions. You should have confidence that they will reliably express vector operations in a map that closely maps the vector instructions available for that system. And finally, we want graceful degradation. So sometimes you will run on a system that will not be capable of running vector operations, and we want whatever you wrote to be no worse than if you had unrolled this and run it sequentially. Now, the last 3 JEPs from JDK 20 come to us from the project that's going on in Loom. Project Loom began in late 2017, and it aims to make it possible to write Java programs that handle I/O-bound tasks in a way that is easy to read, understand, and debug, but also match the performance that is currently associated only to more complicated code, such as that uses reactive frameworks. Before we dig in, let's try to explain why we started looking into a way of having lighter threads. If you have an extremely simple system with a single core and a task that is CPU intensive, then you just use a single thread and you'll have all your CPU properly utilized all of the time. But modern computers are not single core. The norm now in anything except like the most simple device is to have multiple cores. In our example, if this system has 8 cores, then a single thread running one of those cores will keep all of the other ones idle. So, simple solution, if we can split the task, we can do something much better. We could create up to 8 threads, and if all of them are doing CPU-intensive tasks, then those 8 threads will give you 100% CPU utilization, and we can do the work 8 times faster. Now, adding more threads, if your limiting factor is the CPU, will not make this go any faster. We only have 8 cores. This is what a CPU-bound application looks like. But what if those threads are not using the processor all of the time? What if the threads are only working half of the time? Then those 8 threads will keep my CPUs at only 50%. So what could we do? Simple, right? We could double the number of threads per CPU. And now, since each one is working half of the time, with 16 threads, we keep our 8 cores happy. And if the threads were working only a quarter of the time, well, you need 32 threads. You can see a pattern, right? If you had a thread working 1% of the time, then 99% of the time they're waiting, so you can have 800 threads in our 8-core system, all doing profitable work. Now, if this sounds a little extreme, systems on which the task is waiting most of the time are actually pretty common, right? That's what we call an I/O-bound application. If your threads are waiting for something that's, say, from the network, then 1% of the time could even be too much, right? You probably could be talking at 1/10,000th of the time. That's what your threads would be working on. Now, if it was this simple and you could just keep adding threads forever, we wouldn't be having this conversation, right? But at some point, the CPU ceases to be your concern. The current Java concurrency model tells you to use 1 thread for every task. And then behind the scenes, Java will create an OS thread for each one of those Java threads. Java will make it possible for you to use OS threads without having to learn the idioms of a particular OS thread for a particular platform. But the operating system threads are relatively expensive, right? Each one will require a couple of kilobytes of metadata, but they also will reserve about 1 megabyte of heap, whether the thread needs it or not. This in practice means that for most platforms, you will be limited to a few thousand threads. And even though that will be plenty for a CPU-bound application, it's going to be too little for an I/O-bound application. Okay? So, if we're limited by the number of OS threads, before Loom, we have 2 options, neither of which was really good. We could use the Java threads and assign 1 thread to each request. This will make the code easy to read, and all of the debugging tools that are built into the JDK will work just fine, right? If you get a stack trace, you will read it, and it will make perfect sense. But you will be wasting resources. You won't be able to use all of your CPU. And there will be a lot of memory that's allocated and not really used. Or you can code around this 1 thread per request restriction and make it so that a single OS thread can handle multiple requests. This can be done using tools and frameworks like reactive frameworks. Doing so will lead to much more requests being handled by every OS thread, so much better CPU utilization, but it comes at a terrible price. The programming model is now very unintuitive. It is very easy to get it wrong, and if you do get it wrong, all of the debugging tools that you're familiar with will not work. I mean, they'll work, but if you get a stack trace, it'll be impossible to figure out what's going on, or near so. I'm sure somebody here could do it. I certainly couldn't. JDK 20 will bring back virtual threads for a second preview. Virtual threads are lightweight threads that will allow a Java developer to continue using that familiar 1 thread per task mode, so you can write code that it's easy to understand and it's easy to maintain. From a developer point of view, a virtual thread is very similar to a Java thread. But behind the scenes, it is no longer tied to a single operating system thread. virtual threads will allow us to achieve near optimal hardware optimization without asking us to change the way that we code. When we use virtual threads, all of the tools that we've used for debugging behave as they did with regular threads. So that's good. For most developers, switching to virtual threads will require switching from platform threads to virtual threads. Pretty straightforward. They are assigned by the VM to a carrier OS thread only for as long as they need the CPU. When the thread waits, the JVM will pause it, unmount them, and assign the carrier OS thread to some other virtual thread that is ready to get some CPU work done. Later, whenever our first virtual thread needs the CPU again, the JVM will assign it to whatever OS thread happens to be available at the time. It could be the same one, or it could be a different one, and nobody cares. Now, there are two scenarios on which a virtual thread cannot be unmounted because they're blocking, right? It's when it executes code inside a synchronized block or method, or when it's calling a native method or a foreign function. So the Java team has spent a lot of time and effort updating the code of the JDK itself so that within the Java libraries, we don't have this problem. Still, some of your own code might still have this situation. So now, as part of the work to do Loom and to test it, a small group of people from the Helidon team, and by small, I mean one person full-time and one person half-time, they collaborated to create a prototype replacement for Netty called Warp. Now, Netty is used for high-performance protocol servers and clients. Now, Netty doesn't use the model of the simple one thread, one task per request. But it has its own set of APIs to allow to multiplex those shares. Now, Netty has been around since 2004. It's actively maintained, so it has about 18 years worth of hard work and optimizations. Using Loom and very dumb asynchronous code and a little tuning, the Helidon team was able to get similar performance in just 6 weeks. Right? And more importantly, the code for Warp is much easier to read, maintain, and understand, and debug. Right? We got a nice quote here from Thomas Longer from the Project Helidon team about how they never encountered some of the problems that they expected to run into when they were doing this. Now, because they're real Java threads and not some other abstraction, existing code will just work when running on virtual threads. They work with thread level, they give you the same stack traces and the same thread dumps, and with the same debugger and profiling tools. This graph here shows Jetty. Remember that I said that you could just create more threads, right? Well, if you tell it, let's try to run it and say, at most, I want to create 200 threads, right? Now, there's a task, 100 milliseconds IO bound. You can see how, in the little blue one here, the first tasks, everything looks fantastic. And then eventually you run into the point where I really needed more threads. So the latency of the threads just, like it falls off a cliff. All of a sudden, everybody's waiting for the threads. Now you can postpone that. This uses a certain amount of memory, but you said, hey, I got a lot of memory. Instead of 200 threads, why don't I give it 800 threads? And sure enough, if you do that, you can see that you can handle a lot more requests, but eventually you go into the same problem, and this uses a heck of a lot more memory, even though your program may not need it. Now, using Loom, there is a line at the bottom that's barely visible. You can create as many threads as needed. We couldn't get it to the point where it would just be waiting. So you can see here that, that's what you want to see. It just continues creating threads, as many as you need. Now, a great deal of the work that we did on Loom had nothing to do with stack swapping magic or anything. It was clearing the roadblocks in the JDK. So we had to find all of the places in the JDK where blocking might happen and replace it with logic that if it was running on a virtual thread, would pause the virtual thread, free up the carrier thread, and make it available for somebody else. Much of this was done in earlier JEPs. So if you go and look around in JDK 13, 15, and 18, we re-implemented several libraries looking forward to this. This also had the benefit of making sure that some of the old code that we had in those libraries could be cleaned up. So in the end, Loom made almost no significant changes to the JDK APIs, except for the new structured concurrency API that we will see in a minute. But it provides better implementations of the existing familiar abstractions. So if you wrote your own code using threads, you might need to do the same thing that we did and find all of the places where your code won't play nice with virtual threads. So in order to help you with that, there is now a JDK flight recorder event that is emitted whenever a thread blocks while it's bidden. And we have properties to, when that happens, give me the full thread or give me just partial stack. So hopefully that'll help you clean up your own code. Now, since we expect code writing with Loom will have many more threads, we also need to improve how data is passed from the caller to the callee. Developers have traditionally used thread local variables to help components share data without resorting to method arguments. Now, despite looking like an ordinary variable, a thread local variable has multiple incarnations, one per thread. And the particular incarnation that is used depends on which thread calls get or set. Unfortunately, they have some numerous design flaws that are impossible to avoid. Every thread local variable is mutable, right? So it allows this in order to support bidirectional communication. But this can lead to spaghetti code. A second problem is that they have an unbounded lifetime. Once a thread is set, the incarnation is returned until the thread dies or the developer calls remove. And many developers forget to call remove, so memory just keeps getting wasted. And finally, they have some expensive inheritance, because if you grab a thread and you inherit it, the new child thread will have to allocate memory for all of the parent thread's local variables. Now, it's much more common to need a one-way transmission from one component, from caller to callee. And if we accept that constraint, and don't have bidirectional communication, we can use scoped values, which are dramatically more efficient for this purpose. JDK 20 also delivers APIs for structured concurrency. Now, the principle for structured concurrency is quite straightforward. When there's sequential code that splits into concurrent flows, they must join back in the same code unit. If you write code in this way, then the error handling and cancellation can be streamlined, and it makes it much easier to read and debug. So like structured programming codified best practices into the language for sequential code, structured concurrency does the same for concurrent code. Let's take some sample code. The principal class of the structured concurrency API is structured task scope. It's the first variable here in orange. This class will allow developers to structure a task as a family of concurrent subtasks, and you can coordinate them as a unit. Now, the subtasks are executed in their own threads by forking them. That's the scope fork, the next orange, and then joining them as a unit and possibly canceling them as a unit. Now, when you have it written like this, understanding the lifetime of the threads is easy. Under every condition, the lifetime is confined to the body of the try with resources statement, right? The use of structured task scopes ensures that if either the find user or the fetch order subtasks fall, the other will be canceled if it has not yet been completed. If the thread that's calling the parent, the handle, is interrupted before or during the call of the join, both forks will be canceled automatically for you. And you can clearly see the structure here, right? You set up the subtasks, wait for them to complete or be canceled, and then decide whether to succeed or fail. And if the subtasks are already finished, there's nothing to clean up. If you need to debug this code, a thread dump will display the task's hierarchy. So you will be able to find user and fetch order as children of this scope. Because it follows the discipline of waiting for child tasks, some of the most error-prone aspects of cancellations and shutdowns are dramatically simpler. Now, I hope you've learned a few things about the JEPs that are coming with JDK 20. As usual, if you found any of these explanations useful, all of the credit belongs to the authors of the JEPs. If you want to read more about it, you can go to the OpenJDK page, and there'll be links to each one of them. Each one of those JEPs will have cases that I left out, some technical discussions about why some decisions were being made, and what has changed between the previous preview and the current preview, and lots more. Now, the JEPs are only the largest unit of change in each JDK release. There are many other changes that don't rise to the level of requiring a JEP, even some that required a JEP in the past. For example, the Unicode support for new versions. That used to be a JEP. Now it's so routine that we just call it into a task. Now, if you're a quick reader, you will find some things that may be of interest to you. We are disabling DTLS 1.0. Not to be confused with TLS 1.0, that was disabled in JDK 16. But if you happen to be using it, then you probably want to read more about it. So we have, in the release notes, highlighted these higher level 48 release changes, which I will now cover in detail. Just kidding, you can read those on your own time at the end of this session. But if you do want to learn more about them, I recommend that you look at the blogs from a couple of my colleagues from the Java Developer Relationship team. Sorry. Nikolai Parlog and Thomas Schatz have written some pretty good articles that cover some of the improvements in JDK 20 in more detail, and they're quite fun to read. They have their own websites where they post, so you can have the URLs there. But if you don't want to look them up, you don't want to remember these, just look at our Inside Java aggregator site, and you can find them there. By now, you're all wondering, oh, this is fantastic. Where can I get a hold of JDK 20? Well, you can download it directly under the Oracle no-fee terms and conditions from the main JDK download page in oracle.com. Now, JDK versions that are offered under those licenses don't need a click-through. So that means that we can make them available to you using downloadable scripts. The links that you will get, if you just right-click and say Save Link, you can just paste them into a curl or a wget and automatically use them to download the current version of JDK 20. In April, when we switch to 20.01, these URLs will give you 20.01. So you don't need to go and change anything. You can just burn them in there. There is also a little box over there that explains how to use them and which packages you have, and if you have, if you want to use zip instead of an exe, it'll give you all of the options there. Now, if you prefer not to build them yourself, but you want to grab some Docker images with JDK 20, we'll make those available in Oracle Linux 8 through containerregistry.oracle.com. And if you'd like to build your own images, perhaps you want to tweak them a little bit, the Docker files that we use to create them are published in our GitHub Docker images page. So you can use those as a sample to create your own Docker files. With that, I hope you found this session useful. Now, there's many other sessions later today that will cover 1 or 2 or 3 or more of these aspects in a lot more detail. Sorry. And one last thing. Whenever we organize these events, we want to know what you think of the presenters and the content. So please take a moment to rate my session. We want to hear from everybody. If you like it, I want to hear about it. And if you didn't like it, I also want to hear about it. We rely on your feedback to figure out what kind of sessions you would like to see in future events. So this QR code will open the survey page. Be aware, it's the same survey page for every session. So you will need to type that session ID if you want to identify this one, JV02. With that, good morning to all of you.
We'll be starting in 10 minutes. We'll be starting in 5 minutes. We'll be starting in 1 minute. Introducing Sergey Kuksenko.
Hi everybody, thank you for coming here. And right now I'd like to talk a little bit about Project Loom and particularly about Java virtual threads. And just a short slide about myself. It's not my job titles, it's just what I was doing for a long time. I was working on Java performance, and of course here I'll try to talk a little bit about Loom performance. So right now for GDK 20 we prepared 3 different JEPs which are made under umbrella of Project Loom. It's a virtual thread, structured concurrency, which survives the second GDK. Both these JEPs were in GDK 19. And the third JEP for scoped values. Okay, let's talk about virtual threads. It's the key goal, the key feature of Project Loom. Virtual threads are user mode threads that are lightweight enough so a single Java process could have hundreds, thousands, and millions of them running concurrently. The purpose of virtual threads is to allow to Java developers to create high effective, high throughput servers. First of all, it's targeted for server applications, and at the same moment to allow people, developers, write a code in a simple thread per request style and don't deal with different kind of asynchronous programming. And of course I have to warn you, it's not a final, it's everything that we did for Project Loom. It's a preview API. It's maybe changed a little bit in the future. It could be extended in the future, and of course you can find bugs here. But anyway, your feedback is quite important. That is why we made it as a feature preview. Even before then, we finalized everything. Before talking about what's done in the Project Loom, a short talk about threads. Initially, it was created like Java threads on the top of operating system threads, and there are no such place in Java specification and any other Java place where we have some limitation for threads. Thread in an abstraction, at a nice and useful construct for concurrent programming. But eventually, our implementation came to the fact that each Java thread is just a simple wrapper over operating system threads. And here, finally, we've got an issue. Because of operating system threads, they're expensive. We can't have millions of operating system threads. Typical, the number which allows to work is 1,000, 10,000, but quite rarely more. It's a natural behavior of operating system threads. And it became that from one point of view, we have just an abstraction, just a construct for concurrent programming. From the other point of view, it became a resource because of it's expensive. And somehow we have to deal with that. How to deal with this Just an example how thread is expensive. If you take our Java micro-benchmark harness functions, black hole consume CPU, which does almost nothing, just a little bit. And if you run it sequentially, it takes, as you can see here, quite a small amount of time. If you try to execute it in Java threads, doing fork and join, waiting until all computation will be done, it will require much, much more time. A very, very large amount of time is required. So the community, the people around, its solution was found. If threads are expensive, we need a smaller unit of concurrency. And that leads to asynchronous programming. There are a lot of kinds of different asynchronous programming in different languages, and et cetera, et cetera. But unfortunately, asynchronous programming has some issues. First of all, it's viral. You have to rewrite the whole program to asynchronous programming style. You're losing observability, troubleshooting, debugging, profiling. And concurrent reasoning is hard even with threads, but having larger, more vast amount of our concurrent units, we became it more harder. So, and if we would like to make another language from scratch, like Kotlin, maybe it could be avoided. But Java, it's made of threads. And everything in Java is threads. We have exceptions, and we have stack exceptions. We have thread local variables. All debuggers, profile, everything is working with threads, and it creates really difficult to program, to require more efforts to develop fast enough performant asynchronous programs. And there is a dilemma, what to choose, convenient, fast, easy to way, synchronous way with a blocking API, when developers are happy but our hardware much less utilized, we can provide enough utilization for our hardware, or to use more performant asynchronous programming, but it's more difficult to develop and required more efforts. What is the better? So the project Loom provides the second way to solve the issue with thread expensiveness. We are giving the second way. We are trying to make threads cheaper. So what is a virtual thread? First of all, it's a thread. It's the same thread as before. So you don't you need no care about some other details. And because of it, lightweight threads, Java threads, Java runtime knows how to deal with those threads much better than operating system does, and provide it more efficiently. We have realizable stacks, we have context switching in user mode, and we have, of course, our internal scheduler. The very nice feature of virtual threads is that no need to rewrite the whole code if you want to use it. It's not a synchronous style of programming when we have to do a lot of modification. At the same, we didn't change, we don't change, and we won't change the behavior of classic Java threads. In order to distinguish it from virtual threads, we call such threads as platform threads. The behavior of platform threads remains the same as now, because there are huge, vast of frameworks on other things in Java infrastructure which relies on such behavior. And just a simple picture how it works right now. We have still one-to-one mapping between platform threads and operating system threads, and we have virtual threads which are mapped to execution on some subset of platform threads which called carrier threads, and performing that. Also, we have our own scheduler which schedule virtual threads. And right now, with virtual threads, we are getting ability to make both programmer and hardware happy. Using virtual threads quite simple. First of all, it's a we created a new object with thread builder. You may build thread, tells that we are building a virtual thread and execute it as a usual classic thread before. The second way is we have an executor which manages execution of all tasks inside this executor with virtual threads. It's two simple ways. A little bit about performance. Most of that examples is not relevant, it's just a small micro benchmark, but they will show you the difference in behavior. Let's check what will happen with our do nothing 1,000 times micro benchmark. Again, it's the benchmark when we run concurrently 1,000 tasks and wait until all of them will finish. How much time we require to get the whole results. And here we can see that virtual threads are much better than platform threads, but of course there is some competition with asynchronous programming. Anyway, classical platform threads are too expensive in this way. Let's another example. Let's do nothing, but not for a short amount of time, but do nothing for a long period of time. When our threads just spend time in its thread sleep for 1 millisecond. And here we have another results. And this is results where even platform threads outperform asynchronous programming, but virtual threads are much better. Of course, we should check our behavior on CPU-intensive tasks when we do some CPU computations. This particular CPU-intensive task for 1 millisecond. Here, the results may vary, but definitely, if you will switch to practical applications, I'd like to say that you won't see any difference for CPU-intensive tasks between platform threads, virtual threads, and asynchronous programming. It works almost in the same way. And where we provide a better performance for this, it's of course I/O. I have short examples, numbers for when we read a file from a file system on my. These numbers are got on my laptop, and we just count MD5 hash code for this file. For small file, it even doesn't make sense to do any parallelization based on platform threads in comparison with sequential execution. It works quite fast. And virtual threads and asynchronous programming works even better. Middle-sized file, just here we finally got some benefits from parallelization, but again, virtual threads and asynchronous programming provide much better performance for file and a little bit larger file. Just, I think these numbers quite obvious. But all of that, it were just artificial examples, micro benchmarks. It's not real application. Here's a real application which was mentioned in a previous presentation. It's a Helidon NEMA. It's a web framework. And it's written in a simple style thread per request. All API in that application is a blocking API. And we quickly achieved the performance comparable with well-known and perfectly tuned other web frameworks which incorporate asynchronous programming inside. Here on the chart is a throughput, then higher, bar, and the better. We had one presentation about Helidon here, and we will have hands-ons about Helidon. You may ask many questions. I'd like to tell you a little bit about my personal practical experience with Helidon. As a performance engineer, several years ago, I was working on a new HTTP client, which was implemented in GTK 11. It's a new HTTP client which supports also HTTP2 protocol, and this client was written allow you to use two kinds of programming, blocking API and asynchronous API based on Java util concurrent completable future. I was working on that project. Also, I looked into Helidon NEMA source code and check how it works, provide some measurements, maybe ideas for optimization, etc. And from one point of view, it's quite a different framework, different set of API. From one side, it's client. From other side, it's web server framework. But they have a lot of in common. For example, processing HTTP2 protocol from both sides look like the same. And I have to say that in Helidon NEMA, the code which process different kind of HTTP, HTTP 1.1, HTTP 2, first of all, it's much simpler. It's a straightforward blocking API in a thread per request style. It's much simpler. It much less in size. The number of files, first of all, I downloaded NEMA, I looked into code, and my impressions, saw a few files, saw a few lines of code doing the same as we did before for asynchronous in HTTP client. Maybe it's not implemented yet, but at the end I realized that it was fully implemented and provides much more efficiency for developers how to deal with that. Because of, anyway, sequential programming we understand much better and we work with that much faster. And some examples about performance and a lot of things, it's around a little slow. Little law, it's one of fundamental laws in queue theory and provides, it has a vastly usage in performance, etc. That law, it means that the production of latency of requests and the throughput of our system equals to the number of concurrent requests. It could be just a number of queue, it could be a parallel concurrent number of requests on flight. And there are two key things about that law. First of all, that law works for a stable system. It doesn't work for systems where size of the queue is growing, etc. And the second important fact that law does not depend on any statistical distribution on incoming requests. That allows to use it. And example how to use it. Let's say we have some restricted resource in our system. And it's our first bottleneck, our first resource. We don't meet any other bottlenecks before we stuck into that. And the number of concurrency for that resource is 30. It could be just 30 cores for our application. It could be limit of connections to databases is 30. Just an example. And the time which we utilize this resource is 100 microseconds. We do some request, we do it for 100 microseconds. According to Little Slow, the theoretical maximum available throughput when we meet that bottleneck is 300,000 requests per second. Simple computation. Okay, let's move further. If we are dealing with that resource and we want to achieve our high theoretical throughput limited by this bottleneck by 300,000 requests per second, and the overall time of the request is, in average, is 50 milliseconds, it means we need concurrency equals to 15,000. It means we need, for thread per request style of programming, we need 50,000 threads. That's a lot. It's really a lot, and not frequently we can achieve it. Because of its classical operating system thread is a resource. And here is examples. It's a slide which also you can saw on the previous talk. It shows a little law in actions. It's a practical results which were made for Jetty server when simulate request for 100 milliseconds with some I/O limitations. And exactly according to previous formula of Little's law, you can see that if we set up thread pool for 200 platform threads, we quietly reach our throughput around 2000. If we set up 800 platform threads, we also reach the same maximum available throughput as predicted by Little's law. And using virtual threads, we don't met any limitation by our threads, but number of our operating system threads, and we'll provide higher and higher throughput until we really met the real bottleneck in the future. It's quite important, and a lot of question about is how to move your application to virtual threads. And the first and most important idea that don't write asynchronous code. Use the simple, old-style, non-fashioned, boring, single-threaded code, catching exceptions as usually are doing. It's the better way. And the fact is, the real power of virtual threads is a number. You can't achieve efficiency of Project Loom, just convert 100 virtual threads into convert 100 platform threads into 100 virtual threads. You need thousands or probably millions of virtual threads. Virtual thread will provide benefits only if you have a lot of them. You should convert your task, not a previously thread, into virtual thread. So, virtual threads are not resource now. It's just a logic. It's a business logic, or you may consider it a language construct which allows you to make a concurrent programming. You should not care about virtual threads as before. And of course, you should not pool virtual threads. It doesn't make sense completely. Virtual threads are designed to just do their work and die after that. Thread pools of classical thread pools everywhere, they use not only for reusing threads, don't avoid that expensive creation and eliminations of our objects, but a widely used technique, it's a limiting concurrency. It's a frequent task when we have to limit concurrency of our application by some reasons. And size of thread pool is a normal and classical way to do it right now. You shouldn't do it for virtual threads. Just use semaphores. It's another concurrent construct which is designed especially for limiting concurrency of your application. Don't pull virtual threads at all. Oops, I missed. The second problem is thread locals objects. Thread local objects, they are created for threads, they are accessed only by single threads, and usually they have two kinds of different usages. First and widely used scenario is using thread locals as a hidden parameters for our functions, actions, and everything we are doing within the single threads. We made scoped values for it. I won't talk about scope values today, it's just a preview, but it's a new technique, it's immutable objects which allows for you to interchange any information and data. The second usage of thread locals, which was not intended at the beginning of thread locals design, but widely used in the code around the world right now in Java, it's local caches. We want to cache some expensive objects or objects which we think they're expensive, and we put it into thread locals to provide locality and fast access. Don't do that virtual threads. Virtual threads have a short period of time. We have millions in virtual threads, and using thread locals, it's a really, really bad idea. I observed some experiments where highly effective throughput-oriented applications, server-side applications, with adding thread locals into virtual threads, not platform threads. That application got 20% slowdown in throughput. It's probably should be avoided. And the other problem for virtual threads is pinning. We call difference process inside. When the virtual threads start executing on carrier threads, this process called mount. When virtual threads removed from execution to some pool of waitings, virtual threads is called unmount. But sometimes Java runtime can do that unmount action. Right now, there are two sources of pinning. We pin that virtual thread for our platform threads and eventually to operating system threads. And because of we can't move that virtual thread from execution to unmount it, it's pinned to our thread. And that virtual thread, for example, blocked or waste resources. We are wasting our virtual threads, we are wasting our Java threads, and we are wasting our operating system thread. And there are two sources of this. First of all, not mentioned on that slide, it's a native. If you have native parts of your code and you from the native code you jump to Java, and in Java you want to use virtual thread, that thread will be pinned for execution forever. We can't remove it. We have native frames on the stack above, and we can do nothing with that. The second source of pinning is a native synchronization or synchronized on monitors. Java has two ways of synchronization. It's from the beginning, it's keyword synchronized and monitor stated with every object. And that technique exists since Java 1.0. And a later technique, it's the whole package Java util concurrent logs, which appeared in Java 1.5 many years ago, which also provides a more flexible and more powerful way for monitors. And right now, currently, for current stack, we implemented Project Loom virtual thread only for Java util concurrent logs, log friendly. These logs are Loom friendly, and if you're blocked on some monitor, that virtual thread will be removed. Unfortunately, it's not implemented yet. In case of synchronized work, it will be pinned and not removed from execution. It's a temporal state. We are working on implementing classical synchronization on object monitors fully Loom friendly. Please wait next updates. And even right now, for this, we provide some tracing abilities. You may use GFR, or you may provide property GDK trace pin threads and check when threads were pinned and to avoid it. I'd like to do a little bit warning about total and pervasive migration from synchronized object monitors to Java util concurrent logs package. It doesn't require, it's not necessary to do it every time. You should move from synchronized monitors, native monitors, to reentrant logs only if this block of code doing long I/O operations. If it's just a simple block around some state machine, when we have 5 variables describing state of your computations, you have to synchronize it to make it work correctly. But it's just a small set of changes for memory modification, and from performance point of view, it's not required to move it to new concurrency. And here is a simple short limitation. That's all about virtual threads. We did a lot of optimization inside, how it works. It's probably ahead of topic of this presentation. So if you have questions, we could discuss it. I want to say a couple words about the second JEP. Second, our JEP, it's about structured concurrency, which is still in incubator. What we have right now? Right now we have two kind of ideas, kind of action, how to write code. We may write classical, ordinary, sequential code, which simple, which provide failure propagations, I mean exception, of course. If something failed, you may just throw exception out of there and it's efficient, but it's sequential. And we have a concurrent code which is completely unstructured, failures not propagated, very difficult to understand where we have a source of that exceptions, no short-circuiting things, and etc. And of course, it's everything. This is not stack-friendly, not very, very good for observability and everything. And we're suggesting to use structured concurrency. It's quite a simple class which allows you to execute different concurrent actions from the same scope, wait results, but it provides different kind of failure propagations, short circuiting, like shutdown on failure, or just you do different several requests, but you need only one of them. Also, everything here is provided from a box. It's quite a simple API, and we're mostly waiting your feedback from this, about that. That's all from me about the project Loom. Please read the sections, and do you have any questions? Thank you. Oh, there is a question.
Yeah, I had read something around limitations in terms of pinning virtual threads to platform threads around file system operations.
No.
No, that's not true.
It's not a true. Okay, technically it's true. We still did not implement IO ring fully. We are working on it. When IO ring will be implemented, we will have the quite efficient way to deal with file system. But let's check this slide. Yeah, it's a file IO. And here is time and overall time in milliseconds just to read 1,000 files and to compute MD5 hash. So we have file IO and we have CPU computation inside the same block of code. And even here, virtual sets us better because we know that it's file IO. And if we know, and we know in JDK that we have to block this carrier thread for some period of time, we could compensate it. We could extend our set of carrier thread by a new one. We could compensate our lost possibility of execution. It's all technique that exists in JDK since Java 8 when fork join pool were added. It's called managed blockers, if you heard about that. It allows you to compensate blocking operations inside a different set of platform sets. Thank you.
be starting in 10 minutes. We'll be starting in 5 minutes. be starting in 1 minute. Introducing Stuart Marks.
Good afternoon. This talk is about Java language features. It's entitled the Spring 2023 edition. And so the reason is that this talk is continually updated as we make incremental improvements to the Java programming language. And I'll have a slide a little bit later on that shows you how we do that and how that lines up with the 6-month release cadence of the JDK. Much of the work in the JDK goes directly into the main line. We have lots of bug fixes and enhancements going directly into the main line. There are also several large projects off to the side that have been worked on for a number of years. In particular, they are Amber, Valhalla, Panama, and Loom. So I'm not going to cover all of these today. There are some talks that cover some of the materials in the other projects today. But today, in this talk, I'll be focusing on Project Amber. So what does Project Amber do? The goal of Project Amber is to explore and incubate smaller, productivity-oriented Java language features. And so the visibility of Amber is very high. When you're programming Java on a daily basis, what Amber hopes to let you do is make your programming experience more convenient, more comfortable, and quicker and smoother. So there are a bunch of different features in Amber, and here's actually a subset of them. So there's a lot going on here. On the each row is a different feature that Amber has added or is adding in the process of adding to the Java programming language. And then across the top, you see the 6-month release cadence of the JDK. Now, each of these language features has gone through a couple rounds of preview. So for instance, switch expressions, text blocks, records, and pattern matching for instance of have all each gone through 2 rounds of preview before finally making it to be standardized in Java 17 or beforehand. Oh, sealed classes as well. That's another important one. So those are already finalized in the programming language and have been released already. There are 2 additional features which I'll be talking mostly about today, which are pattern matching for switch and record patterns. And you can kind of tell that there's a theme going on here. There's pattern matching going on. These features are building on top of each other and on top of previous features that have already been integrated into the language. So pattern matching for switch and record patterns are still in preview. They're both previewing at the same time so that we can get feedback from the preview releases and so that we can co-evolve them. So it turns out that instead of some other features have been largely independent of other features in Amber. These 2 features in particular, their design is fairly closely coupled. And so we are previewing them at the same time so that we can work on them together and adjust them to match with each other. So as of Java 20, they are both still in preview. We hope to bring those to a final release in the near future. Okay, so the 2 preview features, as I mentioned, are record patterns and pattern matching for switch. But as a prerequisite for talking about these, I'm going to be talking a little bit about some previous Amber features that have already been put into the JDK. Okay, so the first one is just earlier forms of pattern matching. We'll do a quick review of that because the current features build on top of these features here. So first, a quick review of pattern matching. Okay, so this was delivered in JDK 16, pattern matching for instance of, and so I'll just go directly to the code here. So when you're writing code in Java, you can do a dynamic type check of a variable and see if it's an instance of something else. And this has been in Java since probably 1.0, and this was the pattern here. The first thing you can do is do an instance of check, and that gives you a conditional, that's the result of that is a conditional expression, which you can test with an if statement. And then if you know, for instance, suppose the static type of O is object, and you ask if O is instance of a string. Well, typically you want to operate on that object as a string. And so the next thing you do is cast it. So you declare another variable string s equals cast a string of the O reference. And then you can operate on s as a string, for instance, by calling the length method. In pattern matching for instance of, this idiom that was repeated over and over and over again is now essentially put into the language. We can declare a local variable that as part of the instance of expression. And so O instance of string s is what we call a type pattern. And so what that does is if O indeed is an instance of the string class, then that does the downcast and then binds that reference to a new local variable whose static type is string. Now, within the block, we can use the string s as an ordinary string variable. Now, s is only in scope where it is true that O is instance of string. And so outside the if statement, the s variable is not in scope. So you can never get access to s unless it is actually a string. Okay, so this seems really simple, but I'm going to break this down a little bit here. There's lots going on. So there's a little bit of syntax here. In the type pattern, you would say O instance of string s. And so that looks just like a variable declaration because it is. It's introducing a new local variable s into scope at this point. Now, it's also adding some semantics here, which is it's doing a type test. So can O be cast to a string? Well, if so, the cast is done for you under the covers. And the result of that cast is used to initialize the s variable. And this kind of pattern, as we're calling it, can, at least in the current version of Java, can only occur inside of an instance of expression. So there's three things going on here. We have our syntax, semantics, and a particular location where we can employ these syntax and semantics. Let's see, did that work? Okay. All right, so let's put this into use here. So there's an example in the book Effective Java that talks about how to write an equals method. And so here you can see what is fairly typically an equals method. What's interesting about the equals method is that it's required to take a parameter of type object. And so if you want to use something from it, you typically do this instance of followed by a downcast. So the first thing to do is we check for reference equality just to short circuit that and return true. And then we say, okay, if O is null, or if its get class is, if its class is different from the class of this object that we're comparing it to, then we know that it cannot be equal, so we return false. And then we do this thing where since we know that at this point, it's a little confusing. There's no actual instance of here, but we've already compared the class objects. So at this point down towards the bottom of the slide, we know that the classes are the same. Therefore, it is safe to cast O into an instance of a case-insensitive string. And so we store that in a local variable. And then now we can operate on it as as a member of this class, and so we get its S field and then call equals ignore case on it. So the example here is how if we have a class that implements a case insensitive string, you want to find out if it's equal to another thing. And so you have to check if that thing is a case insensitive string, and if so, then you can extract the data from it and then call the methods like equals ignore case that are particular to the case insensitive string class. All right, now what can we do to improve this code? So you can sort of see this thing going on here. We rewrite this in a slightly different way to make it a little more fit our pattern. So if we set aside the null checks and things, because the instance of expression implicitly does a null check for us. So we can rewrite this equivalently to follow our pattern of using instance of. So we can say, essentially say, if O is instance of a case insensitive string, and then we do our inline cast and then call, actually we don't call a method on it, we access a field of case insensitive string, and then we call equal ignore case on that. So this is equivalent code, but this is still kind of, this is older code. This is JDK 17 and earlier, because we're still using the regular old instance of, and we're casting, and then we're only casting, because of the way this is set up in the Boolean expression, we are only casting if we know that O is indeed an instance of a case insensitive string. So what can we do to improve that? Well, this follows our typical pattern of we're doing an instance of check, and then we're doing a cast. So we can use an instance of type pattern to clean that up. And you can see that here, where we say return O instance of case insensitive string CIS. So there, that type pattern fuses the type test and the binding to the new local variable CIS. Now what's interesting is there's no block here, but CIS is in scope for the rest of the Boolean expression. So what we can do is we can then go on and use it to access the S field and then call equals ignore case on it. Okay, so another item of review that I'm going to go over very quickly is something we also added and finalized in the past, which is records. Okay, so JEP 395 added records. This was also released in JDK 16, so this was finalized already. So what a record does is it's a very common pattern to have a class that just represents some data. And objects are great for encapsulating things. If you want to have operations on that object and to have what goes on inside the object be hidden from the outside world. But sometimes you don't really need that. Sometimes you just want a class to represent a convenient aggregation of data. And so I think everybody's using this same point example. What's a point? A point is an XY value. But before records, if you wanted to have a class that just represented data, you actually had to do quite a bit of work to make it play well with the rest of the Java programming environment. So we look at this class point on the left. It has fields X and Y. There's a constructor that takes parameters and initializes those fields. Then we have accessor methods so that you can get the data out of those fields. And then we have our equals method, which is kind of similar to what I was showing on the previous example. You want to be able to compare this point to some other arbitrary object. So we have to do some null tests and some instance of tests and some downcasts and things like that. And then we need to, now if the thing in fact is another point, then we need to extract data from it and then do the comparison. So that's a lot of work in equals. Hash code is another thing. You need to have a hash code function if you want to be able to store these objects in hash-based collections, and so you have to come up with some computation that combines all the fields somehow. And for the most part, that's arbitrary. If you're combining the data of all the fields, then you just have to come up with some formula that does that. This is a typical one. you can argue about making better hash functions and whatnot, but for certain things, this kind of function is perfectly acceptable, and it will work just fine. But it's something that, again, you have to include something like this, because if you don't, your point or your whatever class you're using won't really work very well in a hash table. And then also, toString is yet another thing. Often you just want some string representation of the internal data of the object. And so you have to include one of those too. So all that code on the left is sort of the minimum bar for just storing a couple int fields. So that's kind of a lot. And so that's what records do for us. On the right-hand side, you can see that entire class on the left is replaced by a single line, record point int x, int y. And the record feature of the programming language provides all of those for you. It provides the accessor methods, it provides the fields, it provides the accessor methods, it provides the equals method, hash code, and a toString method. All right, so what can you do with a record? All right, so let's show some examples of how to use it. So you can create a new point by calling its constructor with the right number of arguments. If you don't provide the right number of arguments, that's a compile time error, because there's a constructor that's provided that mirrors the fields that are declared in the record. You can access the fields of the record, or the components of the record, as we call it. So those are methods that have the same name as the fields. So p.x and p.y are the accessor methods. You cannot assign to fields or components of a record. And so what we call a record an immutable, or more precisely, a shallowly immutable class. So the values of a record are established at construction time and cannot be changed thereafter. Okay, what methods are provided? So as we saw earlier, there's a constructor that takes two values. There's an equals method that's provided for you that compares every field of the other record. There's a hash code method that's provided, and this lets you store them in hash data structures, such as a hash map. And there's a toString method that does something fairly obvious with the fields, turns them into a string representation, and returns the result. Okay, now let's move on to the preview features that we're continuing to work on in JDK 20. Pattern matching for switch and record patterns. So after that review, these new features build directly on top of those earlier features. Okay, so earlier we talked about patterns that were introduced as part of instance of. So here, what pattern matching for switch is taking that same concept of pattern matching and making it possible to use that inside of a switch statement or a switch expression. And so in those older constructs, you gave a value to switch over, and then case labels or case arms of the switch statement or switch expression had to be constants. And so now we're saying, let's introduce the possibility of using a pattern instead of a constant. So let's say we have an object O, and we want to switch over it. We can say case string S. Now that looks exactly like the pattern that we introduced for instance of. And so what that means is it's the same thing. If O is an instance of string, then the downcast is done under the covers, and the variable S is bound to the result of that cast, and therefore we can call string methods like length on that S variable. And if O is not an instance of the string, then this case arm will not be evaluated. Okay, now there's something going on here, because you also might recall that the earlier versions of switch statements and expressions had a restricted set of things that you could use as what's called the selector expression. In this case, it's O. It used to be that you could use only integral values, enum, and string. Anything else was rejected. So now you can, basically what we've done is we've lifted the restriction, so you can still use the integral values, or integral types, but you can now switch over any reference type. So you can put an object in there in order to be able to do type tests on that object. Okay, now, but there's something different here, because in the past, when the case arms were constants, they were all independent. And so you didn't have to worry about it because there was no overlap at all between the different constants in the case arms. But now that we can put type patterns into the case arms, there's this question of order that comes up. And, or it might come up. So for instance, let's look at this first code fragment. Again, O, let's say O is has a static type of object. And we want to see whether it's a string or an integer. And so we can write case string s and have it do something if O is a string. And we can say case integer I and have the code do something different if O is actually an integer. Okay, that's fine. Those are independent, and there's no overlap or conflict at all between those two different cases. Now let's look at the second example. Case string s and case char sequence cs. Now you have to know the libraries a little bit, but it turns out that char sequence is an interface, and string implements the char sequence interface. So what happens here? Well, it turns out there's a complication, which is that one of these cases is a subset of the other. And so which should we do? Should we do both? Or which one gets chosen? And so there's a design process that the languages team went through to do some evaluation on this. Something that some other languages do is they look at all the cases and they say, which is the best match? And that's one way to do it. That's a very precise way to do it, and it's useful. But it also has an odd wrinkle, which is that if you have a whole bunch of cases, the compiler will look over, or the language will look over all of the cases and find the best one. But if you insert something down here at the bottom, it can change the entire equation. And so there's a slight bit of non-local side effects going on here. Whereas if you change one part of the code, it might have an effect on another part of the code. And so the Amber design team decided that the case arms should be considered in order. So let's look at these again. So if we look at the second example, we say case string s. Okay, so if it's a string, then that arm will be executed. And then after that is case char sequence cs. Okay, there are objects that are char sequences that are not strings. So that will catch a different set of objects than the string case will catch. Okay, that sounds reasonable. Now let's look at the third example. Let's consider these in order. Suppose O is some char sequence. Okay, so case char sequence cs. That covers everything, including strings. But then what happens if the case string is down below? Well, that kind of doesn't make any sense now. Should that be caught by the one above? If so, then that means this is dead code. And so that's kind of like in other parts of the programming language. If you write a statement in a method that is not reachable, that's considered a compile time error. So we decided that that should be a compile time error too. So order is significant. So here's what's going on. So in this case, the case string s is not reachable. And the reason is that something above it is a superset and catches every possible case. And so nothing can ever get down to case string s. And so when this happens, we say that the char sequence type pattern dominates the string type pattern. And so if you have something that dominates something below it, then that's considered a compile time error, because maybe you need, what's telling you is you need to think about this a little bit more. So if cases are evaluated top to bottom, if you have a situation like this, then this is considered an error, probably because it's a programming error. The compiler will tell you about this. So if you really want to handle strings one way and handle other char sequences another way, you just move the string case up above the char sequence case. You can also mix in constants here. So a constant is a pattern, but it just matches a specific value in a pattern. So if we want to special case the word hello, we can say case hello and have it do something. And then for every other string, we can just have that handled separately. And so this works just fine. But again, if you switch the order of these, then string will dominate the constant hello. So you can't have hello occur below the case string. And that's what happens, right? Because string dominates the hello constant. And so this is considered an error. Okay, so another limitation of the previous versions of switch, disallowed null. Again, the integral primitives, of course, could not be null, but string and enum are reference types. And in the older versions of switch, if those were null, switch would throw a null pointer exception. And so sometimes you really want to take a reference and do some null testing. And so in the earlier versions of switch, you had to write an if statement outside and deal with it. But here, we, since we're integrating it with pattern matching, it's an opportunity to revisit null handling and see if we can improve that. So the way we decided to do that was to allow adding a specific case for null somewhere in the switch statement. I mean, it's fair enough. So if you want to handle null, then just put in a case null. Now there's this idea of exhaustiveness. So this particularly comes up when you're using a switch expression. So an expression in Java always must evaluate to some value. Now in a switch statement, you could have several case arms, and if none of them matched, then the statement would just fall through and continue with the following statements. You can't do that with an expression. So there's an extra wrinkle going on with switch expressions, which is that the case arms that comprise that switch must be exhaustive. And that means that every possible value that comes in as the selector must be handled by one of the cases. So if we have this here, if we have any object O, we say case string, oh, do something, case integer, do something else. Well, now what happens? What if it's neither a string nor an integer? Okay, the expression needs to provide a value, and that type of being other than a string or integer is not handled here. So this is considered a compile time error. A switch expression must be exhaustive. So how do you make something exhaustive? Okay, well, it's pretty easy. Just add a default case. Okay, so now it's exhaustive, and so this works just fine. Now, revisiting the switch statement. I said earlier, in the earlier versions of the switch statement, the cases did not need to be exhaustive. And that's something we cannot change at this point because there's too much code out there that relies on the fact that it's possible to write a switch statement and have it match none of the cases and fall through, or fall off the end. And that's okay, that code needs to continue working. However, it's a common source of errors, right? So if you're writing a switch statement and you forget, or if you forget something, or if you know, in one part of the code you add the possibility of passing in a new value, but you forget to update the switch statement, then that introduces a bug there. So sometimes you really do want even a switch statement to be exhaustive. And so what we're doing is we're saying, okay, if you are using type patterns in switch, even a switch statement must be exhaustive, in addition to the switch expressions, which always must be exhaustive. So that's a way we're making the language a little more bulletproof. Now, what if you wanted a switch statement and you wanted to fall through if object, for instance, is not a string or an integer? Well, just write a default value in. That way you're explicitly saying, okay, I am handling this particular case by ignoring it. So that's manifest in the code, and we believe that will prevent a certain class of errors in using the switch statement. Okay, so this brings in another of the previous Amber features that I mentioned earlier, called sealed classes. And sealed classes play into the exhaustiveness story. So here, in this example, we have a sealed class shape, which is abstract, and it permits 3 subclasses, circle, rectangle, and square. And you can see the circle, rectangle, and square classes right there. Now let's just think about this very simple class hierarchy for a moment. If you have an object, or if you have a variable of reference type whose type is shape, what can it be? Okay, well, it can be null, or it can be, it can't be a shape because shape is abstract. And what sealed class says is that these classes listed in the permits clause are the only ones possible. So you can't have some code elsewhere that says class quadrilateral implements shape or extends shape. That can't exist. That will not be permitted because there's a permits clause that says only these three can be permitted here. So, so what does this buy us? Well, so if we are switching over some object of type shape, then when it gets into the switch statement, we can have cases for circle, rectangle, and square, and and we're done, because we know that those are the only possible cases for an instance of shape. So we don't need to put a default clause in there in order to make this switch be exhaustive. Okay, there's some other things that we've added to switch expressions, switch statements and expressions here, but basically it's an adjoint to the pattern switch, which is sometimes what you want to do is you want to do a type switch on, you want to do a switch on the type of the object, and then you want to do some additional things like checking the values, right? So we have some arbitrary object O. If it's an integer, okay, great, we know it's an integer, but if it's negative, we want to do one thing. If it's 0 or if it's positive, we want to do something else. And so what happens quite often is that you have a case, and then inside the case you have some if statements. And so really, it might be nice to break those out into kind of, you know, the same level as the switch statement. So we can say case integer I when I is less than 0. And so that's sort of integrating a Boolean expression that we're calling a guard clause into the case arm itself. And then you can have several of those. So if we want to have a negative, something that handles it negative, something that handles when I is 0, and then the rest of them are caught if we just have an unguarded case integer I as the third case arm there. So now we're handling not only the cases where O is an integer, but different kinds of values for what that integer is using the when clauses. Okay, now moving on to the next feature that we are previewing in JDK20, which is called record patterns. And so you can see these are all building on each other. We've talked about patterns several times, and we talked about records a couple times. Now we're combining them, and so you can do record patterns. And so the salient point of a record pattern is not only can you do a type test, but once you've established that an object is of a particular record type, the language knows what fields there are in the record. And so you can pull those out and bind them directly to variables at the point where you're doing the pattern matching. And so you can do that both for switch and for instance of. So let's create our point, new point 3.4. And so now we can say, if E instance of point X and Y. So this is interesting. We sort of are adding arguments to our pattern matching syntax here. And we can do the same thing with the switch statement. So instead of just saying case point P and then do something, we can say case point int X int Y. And so what that does is, instead of just binding P to a variable, what it does, it breaks open the records and say, okay, we know that a point has an X and a Y, and so let's take those values and bind them to new local variables right here and introduce those variables into the scope from this point onwards. All right, so let's show this in action. So this is a somewhat involved example. I'll take a little time to go through this. Okay, so we have our record, our point record. We have a color, and we're introducing a new record, a colored point, which is a point combined with a color. Pretty simple. Now, suppose we have a task where we want to say, let's print out the horizontal position and the color of some object that might or might not be a colored point. Okay, so prior to these new preview features, how would you do this? Okay, so we have our object O. We say, okay, so if O is instance of a colored point, we do our typical thing. Now that we know that it's an instance of a colored point, we do our downcast and store that variable in a new CP local variable. And again, we want to get the X component of the point contained within it. So what we have to do is pull out the point from the colored point. So we call cp.p to get the point. But we have to null check it there, because in case it's null. And so if it's null, we'll just return. So let's set aside what to do about that case, because we really do not want to call any methods on a null reference. Now that we have a point in P and we know it's not null, now we can call the X accessor method on it to get the X value out of it. So now we can, oh, and there's something missing on the slide actually. So we need to we have the X value, but when we print out the color, we need to call cp.c to get the color value there. Okay, so we can see a bunch of things going on here. We do some instance of checking, we do some downcast checking, and then we do some extraction in addition to downcasting the variable that we verified was the right instance. Okay, so what can we do to improve this code? So one thing we can do is we can turn it into a switch pattern. So we can say switch O case colored point CP. Okay, so that gets rid of some of the instance of downcast stuff. And then now that we have a colored point, then we have another instance of here. So if cp.p instance of point P, so we're doing kind of a nested instance of pattern here. So we're downcasting we're probably pretty sure that if it's non-null, it's an instance of point. But what instance of does is it also does the null check. So inside of this inner if statement, we know that P is a non-null reference to an actual point. Okay, good. So now we can call p.x and cp.c to extract our horizontal location and color. Okay, so that's good. But we can do a little bit better. So notice here that we're doing an instance of check followed by a call to an accessor. So how can we combine those? We're using this new record pattern syntax to extract the components of the point record and bind them directly to local variables. So we're saying if cp.p instance of point int x int y. And so now we have x and y variables, and we can just use them directly. We don't have to get a kind of an intermediate variable that stores the point and then call methods on it to extract it. And then we just use x where we want to when we're printing out the horizontal location. Okay, but again, we can apply this this idiom again. Case colored point CP. All right, so now that's just a type test, but we can do an extraction because what do we do with the CP variable? Well, we call an accessor to get the point, and we call another accessor to get the color. So we can combine those into another record pattern. So we can say case colored point, point P color C. And so that extracts the point and the color components from the colored point into local variables, and then we can just use those variables directly. But notice again that we still have some things going on here. We've extracted the point from the colored point, but then we turn around and do an instance of to extract things out of that. And so we can actually nest patterns. And so we can take that point int x int y pattern and nest it inside of the colored point pattern. So now we say case colored point that contains a point int x int y and a color C. And so now we've taken a nested structure and extracted a bunch of things and bound those values directly to local variables without having to do multiple steps of open up something, look at it, oh, is this an instance of something else, look at it, pull things out. So we're doing all of that in one switch pattern here, one record pattern that combines the instance of check, it combines the downcast, and it also combines that with the extraction of values of record components. And then, now that we have X, Y, and C, we can just use them inside of this block, and it works just fine. All right, so that's what we're working on for JDK 20. Those are currently in preview. There's actually a whole bunch of other stuff going on in Project Amber as well, and I don't have time to cover all of these, but you can look on the OpenJDK site and see what's going on with them. There's string templates where we can interpolate string values inside of a string. There's what we're calling the on-ramp, which is a way for students and beginners to learn Java more easily without having to deal with boilerplate code. Unnamed patterns, that's something that's also being worked on. So you saw a couple examples there where we wanted to find the horizontal location of a point. So we said point x, y. Well, if we don't need the y location, then why do we have to have a variable for it? So we're coming up with a syntax for saying, okay, extract something, but I actually don't care about this particular value. So the proposed syntax for that is to use an underscore. There's some things about using instance of for primitive values. So currently instance of works only on reference types, but sometimes it's useful to do the downcast stuff for a wider primitive into a narrow primitive. Sometimes you have an int that you know is within range, and so if you say instance of byte, then you don't want to have to do some fancy masking and checking in order to make sure that the cast you're eventually going to do is safe. Also, we're thinking about ways to use patterns in more places. So right now, patterns can be used in instance of and in switch. And so we're considering to have a statement that can invoke a pattern match somehow. And so the draft for this uses a new keyword called match. It's probably going to turn into something else, but that's what the team is working on right now. And then another area of where a lot of investigation is being done is with pattern matching and extraction of regular classes, not just records. And so this is going to be a lot of work, but it's going to be extremely valuable. So so the thing about records is that you're telling the language exactly what components are in it. And so the language can do the extraction of those components. But you might want to have your own class and say, hey, I want to make my class available to the pattern matching construct, and I'm going to provide these values. And so there's a whole bunch of work that needs to be done, but that's something that's being worked on as time goes on. All right, so Project Amber is doing a lot of different things, a lot of different features, some of them independent and some of them dependent, like these whole series of pattern matching features. The idea is to make developers more productive, so there's less noisy boilerplate code to write, less error-prone code to write. There are lots of things going on all at the same time. Because of the 6-month release cadence, the platform is moving very fast. So every release, there's new features or new variation of an old feature that's been in preview. And so we're making continuous improvements every release to the JDK. All of this stuff is public. Go to the OpenJDK website. There's mail to the mailing list. You can read the JEPs. There are early access builds for things. Try them out, write programs, tell us what works, tell us what doesn't work. All right, before I finish up, there's a survey that I'd like to have you take. If you have a chance, please snapshot this QR code or take a picture of it. And when you go to the website that this QR code references, then please enter session JV08 to give feedback on this session. Oh, one more. Not quite yet. So the final slide here is JDK 20 is available today, and you can download it from here. Thank you.
We'll be starting in 10 minutes. We'll be starting in 5 minutes. be starting in 1 minute. Introducing Paul Sandoz.
Thank you. Welcome to this talk on Project Panama. I'm Paul. This talk was originally written by Maurizio, the architect in charge of Panama, but unfortunately can't be here. But any mistakes you see, you blame me, not Maurizio. Okay, this project has been going on for quite a while, about 6 years now. When it first started out, we weren't really sure what we were doing, and it was a bit researchy. And it often focused on the wrong things. Originally, it was very tool-centric focused. But as we started to iterate on it and to put stuff into the JDK through something we call incubation, we got feedback and we learned more about it, and then things started to crystallize around primitives. We like to talk about finding the right primitives for the feature we want. And things started to crystallize around 2 APIs, and then they joined together into one API called the foreign function and memory API. We iterated on from that a bit, and then we up-leveled it to the notion of a preview, which means we think this is actually pretty solid now, but we reserve the right to change and do a bit more feedback on it. But all the concepts almost crystallized, and it was really about getting the API points right and the naming right and so forth like that. And now we're at the point where it's getting more solid and more crystallized, and we're almost ready to go final, but not quite. Probably 2 turns of a crank more. Now, after this talk, if you're interested, I recommend you read up on the new JEP 442. You can just put that into a search engine. It should pop up. It contains a great description of all the features, some of which I'll touch on here in a great explanational way, which I think you'd enjoy. This is probably pretty close to the final thing we'll see. But if you're interested, I urge you to try it out and give us feedback, because this is the iteration cycle we've managed to do to improve this over these number of years, is through this cycle, getting feedback and feedback, so that when it goes final, we are comfortable supporting this for the next decade or more. Okay, so what is the motivation here? There are lots and lots of libraries out there that are not written in Java, surprisingly so, although I would like more to be written in Java. That's just not the reality. And we'd like to use those libraries. And you should be able to use those libraries, and it should be easy to use those libraries. But it's not so today, and we'll get into why. What libraries would you might want to use? The linear algebra libraries. I think a lot of people might have in their minds machine learning kinds of libraries. We see how in the world of Python, it's really easy to slurp in native libraries to effectively wrap around a native library that performs some form of machine learning in a developer-friendly way. I think that's the sweet spot that Python has. Perhaps we can do that in Java too. So, not just machine learning libraries, there's graphics processing, there's I/O libraries, the JDK itself needs to use native libraries and so forth like that. Maybe we can use the JDK with Project Panama too. So there's a lot out there. We should be able to ingest it and use it efficiently and quickly. At the moment, we have one option for this. It's called JNI. If you had asked me, should you use JNI? I would say, with caution and care. If you don't have to use it, don't use it. I've wanted to use it, but it comes with a cost and a certain activation energy to use it, so I've avoided it in some of my projects because it's just too much work. JNI allows you to call native methods, C methods in libraries, but it's a lot of work. You have to specialize your methods with native, no body, let the Java compiler compile that. It generates a C header for you. You compile that C header using your native toolchain, and then you implement those methods in the C header using a native toolchain as well, using JNI API. It is a lot of work. I don't know if you've ever tried this, but it's very error-prone. You're out of the domain of Java. You're now into the C world, and you have to code against that, writing your own C code. You've added another form of compilation to your project, and it's very easy for bugs to slip into this code and crash the VM. And it's hard to reason about, hard to debug. And it's pretty cumbersome to pass data from the Java world to the native world using this API. It can be inefficient. Not only is it easy to have bugs that crash, it's easy to have performance bugs here too. It's just too hard. And in fact, perhaps the original designers of JNI wanted it to be hard as a goal, because when Java was first designed, they didn't want people writing stuff outside of Java. They wanted people to use Java and only Java. So JNI was a necessity, but it was deliberately hard to do so. We don't live in that world now, thankfully. So JNI allows you to call native methods, but what do we do about data? And so there's data that's not managed by the VM, not managed by the garbage collector, which we often call off-heap data, which sometimes you need to allocate and then pass that information over to the native layer, or the native layer needs to return memory to the Java layer so they can interoperate together. And at the moment, we have something called direct byte buffers that do this. And this allows you to interchange objects that are called byte buffers that are allocated natively using native memory, and you exchange those across the sort of native layer. And this is okay, but not perfect. And so there are a bunch of problems if you've ever used the byte buffer API that's supplied by Java. One is it was designed a long time ago, and it had the right design constraints then, but it's showing its age. There is very little you can do to control the allocation of a byte buffer. You can ask it to allocate natively a direct byte buffer, but you don't get to control the management of that memory. It's up to the VM to do that. Or you can go through JNI, and JNI can allocate that byte buffer where it stamps in an address and size. Again, you don't get to control that. So you can't necessarily explicitly free a byte buffer. It's up to the GC to do it when it's ready to do it, so you may have a resource issue. There's also a big thing here, which is a huge limitation, which is you can only address up to 2 gigabytes in size for a byte buffer, which means if you're doing slurping in large language models and trying to interact natively through Java, often people have an array of these things to manage them and abstract over it. It's horrible to do this. And it's also inflexible in terms of its indexing and addressing. It has state inside there that you can index in a relative fashion and update the index as it goes. So the buffer carries state with it. It doesn't just have the address of what it's accessing and a size information. It has a little index with incrementing. So it's not immutable. It's mutable, which makes it harder to optimize. A case study here is TensorFlow. It's indicative here. TensorFlow represents a complex native API. I don't think TensorFlow represents a native API you want to use today for machine learning, in my opinion, given the way the TensorFlow community is going. I think one should look at ONNX or ONNX initiative for that, but it's indicative of a complex native API with lots of native functions, structures, constants, and so forth. The TensorFlow, the community there wrote a binding for Java, and I don't know when this was exactly snapshotted, but the relevant information here, when they snapshot it, was there was over 3,800 lines of native code and almost double that, slightly less, for Java code to develop this native binding. And that's a heck of a lot of work. And the bugs are lurking in both that set of code. Trying to manage and debug that is hard. It's a lot of mechanical work. And every time you update the API, you have to incrementally update this. That's the same for any complex native library you might want to integrate with. It's a lot of work. And possibly when you've integrated it at that level, you've only got to the idiomatic level of what the C API offers, and you may need to go high level to make it idiomatic in Java. So developers use third-party frameworks to do this, and some of them pretty good. Some of them are opinionated in what they do. But if we can sediment this down into the JDK, we can do this better, and then an ecosystem of tooling and libraries on top can build on top of what we do. So enter Project Panama. It's aiming to make a better version of JNI effectively. We want to replace JNI with a mechanism to call foreign functions, link to native methods, and interact with native data efficiently. The analogy of Panama comes from our resident VM architect, John Rose, who had this analogy that when we built the Panama Canal, it enabled faster, cheaper commerce between two different worlds. Before that, you had to take a perilous journey down past, around the tip of South Africa, past Cape Horn, and all the way back up again. And that's analogous to what you do in JNI. It's perilous to write JNI code. It's a long journey to do so. Can we make this better? My analogy is, can we do as good as or better than Python in terms of interacting with native libraries? And I think we can, and I think Panama can achieve that. So what we'll do is we'll replace the byte buffer concept with a new concept, a new API that's better at interacting with native memory, faster, cheaper, safer, and a way to interact with native code, faster, cheaper, safer, and a way to sort of take account of that mechanical process, provide tooling on top of the APIs to help you with that mechanical process. So here's the architecture at a high level. So at the bottom, we have the JDK, and we had two new APIs, the foreign memory API and the foreign linker API. Sort of pretty clear what they might do. One interacts with memory, and one interacts to link native methods or link methods that are outside the JVM. So foreign means not in the JVM, it's outside. So we could interchange foreign with native too, if we like. Those two APIs, they actually depend on other primitives within the platform and build on top, we'll talk about later. They're called var handles and method handles. So when I talked about finding the, what we like to do is find these primitives, and they turn out to be, if we get them right, they turn out to be useful in ways we didn't expect. And here is one way that I personally didn't expect that these APIs would be designed. They leverage var handles to interact with native memory. The foreign linker leverages method handles to interact with native methods. And we build on top these abstractions. And from there in the JDK, we can build on top further. And this is where we can add tooling support. That Panama comes not in the JDK, but as a separate accessible download, a JExtract tool, which you can point at a C header file, and it will analyze that C header file, parsing that C header file, building an AST tree for it, and then from that tree of descriptions in the header file, use those two APIs and generate Java code for you that binds to those APIs. So you don't have to write the mechanical code. And then after that, you can use the Java code generated to do the creative part. Now, the creative part may mean that you're using this for some internal function, or you may decide that you've got a native library out there. You say, hey, I want to use that in Java, but I want to use it in a Java way, not a C-like way. If you just use the low-level native bindings, what will come out in your code is something that looks like C. You wrap that around, and you create an API that's idiomatic to Java, using all the modern Java features that, for example, like Stuart talked about in Amber. And that's the creative part. We effectively get a huge leg up by doing this. You can iterate a lot faster, you can get started a lot faster, and way, way faster than JNI doing this. So we lower the entry point in, cheaper, faster, easier, safer. So what is the foreign memory API? So it's a way to access memory across a variety of memory sources. There's a notion of something called a memory segment, which models a region of memory. You can think of a memory segment as an immutable object that contains a number of things. One is an address, where it points to a memory. One is the size information of how many bytes from that address, that region, can I access. that gives you spatial bounds. So if you access less than the address or greater than the address plus size, you'll get an index out of bounds from it. It also has something called temporal information in it, that the memory segment covers may be alive or may be freed. And so there's a temporal constraint of this memory segment, or it comes with a lifetime. If it's alive, you can access the memory. If it's not alive, you'll get a legal access exception that says the memory is no longer there anymore. So you don't get any use after free cases from that. And then there's the notion of confinement, which means that, am I allowed to access the memory here? And we confine based on a thread. If you create a memory segment that's confined to a thread, only that thread can access it, and not other threads. So if you're trying to control immutability, you can do so, and you can ensure that another thread won't get access or you get a runtime error. When we have a memory segment like this, we can also describe the contents of that memory segment programmatically by using a layout. So we can build up a recipe. What is the contents of that memory segment? So this is the way we describe native structures, native unions, arrays, and so forth like this. And we can use something, a lower level primitive in the platform called var handles, which allows you to peek and poke at the memory in the memory segment. Now, there's easier ways to do gets and sets on memory segments themselves, but if you want to do complex traversal through the structure as defined by a memory layout, you can get a var handle and get access. So you don't have to do all these addressing calculations yourself to get access to the memory. Again, these are low-level primitives we expect others to build on top of to make it even easier later. I will explain some of that now. So here's a really simple example of how we might model a struct that's containing two doubles, say it's a .2D structure, and it's filled in with a certain value. So we want to create some memory. So what we do is we use an arena, which allows you to control the allocation of memory. And we're going to create an arena that's confined, which means all the memory in here is only accessible by the thread that created the arena. And we're going to wrap it around a lifetime. And the lifetime is represented by the trie with resources. So within the trie with resources, the memory that's allocated by the arena is alive. And outside of it, it's no longer alive. And within the trie with resources, we can use the arena and we can allocate memory. In this case, we know what the size of a struct is. It's two doubles, so it's 8 times 2. And we allocate a memory segment, which is allocated into the arena. I can allocate more memory into the arena if I want to, and I can the memory within the arena, the different allocations can point to each other too if they want to as well, because you can think of it as a unit. Then I can use sets and gets on the memory segment to set the first element, the x element, because we know it's at position 0, value of 3, and then the second element we know is at position of 8 bytes, the value of 4. And then when the trie with resources closes, the arena is closed, and the memory that was allocated within the arena is freed up. Like so. But we can do better than this. This addressing calculation is where bugs can reside. So we want to access memory in a structured fashion, like in C, when you can say point.y. And we don't want to manually compute the offsets. That's where bugs lie, as I said. So we can describe, using memory layouts, this programmatically. So in this example here, we got that structure .2D. We can describe it effectively as a tree. So we can say, I'm building a struct layout, and it says it's two values, and we can give them names. So it's a structure with X and Y. So we're building out a programmatic description of this information. It just so happens the building out of this tree creates a bunch of interfaces that are sealed, from which, if you want to, you can use pattern matching on. So we're trying to make sure that whatever APIs we design are also usable by the new language features that we have that are made available, so they become more easily digestible with features like Valhalla. Oops. So we can use var handles here to do this kind of access. Var handles are a pretty low-level mechanism to peek and poke at memory, mostly atomically, but also you don't have to use it for atomic actions if you don't want to. And so memory segments can be dereferenced using a var handle obtained from a layout. Let me show that here. So we got the structure, as before described. Now, instead of accessing the memory directly through the bytes, we're going to create a var handle for each, for the X component and the Y component of the structure. And we're going to appeal to the struct layout and say, hey, give me a var handle for the path element that is associated with the group, an element in the group whose name is X. And the same for Y. And what this does is computes and creates a new var handle that knows the offsets into the memory where to access the data. So I don't have to compute it. So I can allocate my point, and now I can allocate my point using the struct layout because we know what the size is here. It can compute the size. We don't need to specify the size here, hard-coded. And then we can use the handles to access the points. So we've up-leveled the abstraction here. And with these abstractions, we can up-level it even higher if we wanted to and get even easier and hide these var handles through. I think I will expect developers outside the JDK to build abstractions on here to make it even easier. So once we have the ability to access memory natively, like this, we need to be able to call methods with memory we've allocated natively. So the linker in the foreign linker API provides two key abstractions, or two key pieces of functionality. One is to take a symbol from a library, look up its address, and then bind that address to what's called a down call method handle, which when we can invoke from Java. We don't have to write any C code to do this. The runtime will work out exactly what to do. Another thing that's possible from the foreign linker is that sometimes native calls have functions inside them, function pointers, and they call functions natively. And if we want the native to upcall to Java, we can actually bind an existing method or lambda to VM stub, which has a pointer in memory, which when we can pass natively down. So we can make up calls back, and we can make down calls in. Now, when you interact with native code, you require knowledge of platform-specific details. You need to know around size and alignment of types. You need to know if structs are passed by value and so forth like that. So we need to describe the description or the signature of a native method. And to do that, we use a function descriptor, and the function descriptor uses the layout language that I showed earlier, like the struct, the points, or the 2Ds and the doubles, and so forth like this. It uses the arguments of each of the functions, or the parameters of the function descriptor are described using memory layouts. And so is the return type. And once we can do all this and implement it, we can actually get pretty good performance. So down calls are about as fast as JNI. There are some things you just cannot get around doing in terms of transitioning from a managed environment to a native environment. There's a certain cost to doing that, and it's hard to remove it. But up calls are a heck of a lot faster because they weren't optimized in JNI, and we can optimize that route up much more efficiently. And in fact, with the ability to invoke native methods through method handles, it means the VM can actually see more into what's going on. And it means that there possibly is further optimization opportunities when you're making multiple method calls together. Maybe there's a way to coarsen the scope, just like we do lock coarsening. When there's lots of synchronized calls, we can coarsen the lock. I don't know if there's a way to coarsen the scope of where we know there's multiple JNI calls in here to somehow offset some of the cost of each individual call. In some cases, the performance issues of JNI or calling native is not an issue because the native method does some expensive computation. So it may not matter. The offset, the cost is so small compared to the actual computation. So you may not need to worry about it. But up calls do make a significant difference. And I've seen this in native libraries and people binding them to Java and getting good performance in this model. So let's look at a little example here of linking native functions. So we have an example. We're taking our point to tstruct again, and we got a method called distance that calculates the distance of a point from the origin. And we have a main method that instantiates a point value and calls distant with the point and returns it back. Nothing too complicated. If you're going to compile this on a toolchain in Linux, the assembler code would generate a specific kind of assembler that supports the calling convention of the platform, the ABI. And in this case, it has a particular way of doing it. I'm not going to go into the details. But if you look at this on Windows, the details are going to be different. So the linker has to understand what platform it's running on, and at runtime, support the differences in the calling conventions. And it can do this, and it can do it optimally. We can leverage dynamic code generation. We can leverage C2 to optimize these calling conventions, and it can do it really efficiently. And we encode these calling conventions at runtime. So in JNI, you lean on your compiler toolchain to do this, but now we're doing it dynamically. And through the mechanisms of the method handles we extended and the enhancements to C2. So how would we link in Java dynamically using the foreign linker API? So here's an example showing the code in Java to do a similar code in C. So first of all, we need to look up the symbol for distance. We've got a string which represents the distance symbol, and then we need to look up its address. Where does this function reside in memory? So we look it up, we get a memory segment back that is associated with this address. This memory segment is a pointer with 0 size. It just represents the pointer to the function. And then we create a downcall method handle with this address and a description of the signature. In this case, the function descriptor is returning a Java double back as a layout, and we're accepting in a 0.2D layout. So we're leveraging the layouts we did before to build up a function descriptor. And we get back a method handle. You may be familiar with method handles as an alternative to using for reflection. And if you're familiar with that, you'll know how to use these immediately. So now, once we got this method handle, we can allocate our structure as before, as I showed, in a confined arena, set the values of the X and Y components of the structure, and then call a distance function with the point and get the value back. It's that easy to do. No JNI, no C code, no nothing. For simple cases, you can write this by hand. But for complex cases, like we've shown in TensorFlow, you don't want to write this by hand. Not at all. You want something else to do this mechanical work for you. Ideally, you want this mechanical work to be done in a way that's not too opinionated, but it has to have some stake in the ground of how to represent this, because when you have a tool like this, everyone wants their own little feature to be in this tool. That's the danger of it. So you have to come at a certain level that's reasonable and say, okay, we're not going to be opinionated here. If you want to be opinionated, you can write your own tool to do a similar thing like JExtract or build on top of what JExtract does. I expect once Panama is final, people will write their own tools to do something that is more specific or more opinionated to their needs. And we'll see what happens in the ecosystem. I'm going to be excited to see what happens. So what JExtract will do is generate similar code to what I've shown you before in terms of obtaining the symbol, the address of the symbol, obtaining a method handle, and so forth like that. So the way JExtract works is it actually uses Clang to parse a C header file and get a tree of a C header file in memory, and then it analyzes that tree and mechanically generates all the Java code for you. So here's a simple example. Say we have, on the command line here, we run JExtract. We're going to say I'm going to generate the Java source. By default, it will generate class files. I'm going to specify a target package, and I'm going to point it to standard lib. So I'm running this on Linux. And then I may use it like this. So I import the standard lib classes in this package. Here, that was generated by JExtract. I create an arena confined. In this case, I'm going to call the qsort method. And so I want to allocate an array of integers. And here's the integers I want the array to be filled up with. And I'm going to, if you're familiar with qsort, qsort has a callback function to say, how do I compare two elements? And so qsort will do an upcall. And so we want to express how we compare these elements in Java. So JExtract has generated some code to create an upcall stub for me. And all I have to do is pass in a lambda expression that gets given two memory addresses And then I can do an integer compare by doing gets on each of the memory address at position 0. So I allocate an upcall stub. I allocate the upcall stub in the same arena as I allocated the array itself. So once the lifetime of the arena finishes, that memory will be cleaned up as well. The allocation of the stub will be cleaned up. And then I can call qsort with the array, how many elements are in the array, what is the size of each element, and then pass in the compare function that was passed here, which is just another memory segment. It's an address to a VM stub that was generated that wraps and knows how to call back up into Java, like so. And then the sorted array pops out. I wouldn't suggest you would use qsort like this at all. You can use Java sort. It's going to be a lot better. But the key thing here is it's showing this upcall and how easy it is to do and how easy JExtract can let you do this on your own APIs you may want to ingest in. So this is an example of what JExtract might generate. It's sort of sanitized a little bit. I'd encourage you, if you're interested, to actually run the JExtract tool and see what it actually generates. So it generates a function descriptor of the qsort method. In this case, there's a pointer. So JExtract has its own language for the values and the layouts. So we're talking about a C pointer. That's the pointer to the array. A long, that's the number of elements in the array. Another long, that's the number of bytes each element has. And then a pointer to the function pointer, like so. Then there's a lookup from a qsort symbol to get its address. And then we get the method handle. And then we wrap the method handle call in an easier method to use called qsort, which takes in the memory segment that's the address of the array, the number of elements, the size of each element, and the memory segment for the function pointer, like so. So you think of memory segments as pointers here, pointers that come with size, pointers that come with lifetime constraints, and pointers that come with confinement constraints. And when you invoke a method handle, it throws throwable, so of course you have to deal with that. So that's the sanitization that JExtract gives you. It's not too opinionated. It's pretty low level for you to build up on. So this is what you'd have to do in JNI today. Now, if you can't read this, it's okay, you're not meant to. It's just showing you the level, the detail you have to get into when you do this in C, and support the upcall in C, and you have to be a little bit opinionated in how you do this. So I would not recommend you do this. If you can go to more recent versions of Java and try out Panama instead. Bugs are lurking in this code, potentially. So the performance is pretty good. When you compare the performance of doing a qsort using JNI or Panama, the performance is much better with Panama. Lower is better here. You shouldn't necessarily trust performance numbers presented on slides. So if you're skeptical, do it yourself using the Java microharness benchmark to measure this, and you should get similar numbers. Reason is that upcalls are much more efficient in Panama than they are in JNI. So back to TensorFlow. Instead of writing all of this C code and Java code manually, we can point JExtract at this code instead. And once we do that, it's going to generate a lot of classes or source files, compile them, and then we can call TensorFlow, just a simple example here, just to get its version and get its string out like that. It gives you a leg up so that you can immediately start playing. Now, the API that's produced in Java is going to mirror the C API that's in TensorFlow. That may be useful for your purposes, but if you're going to offer that to developers, you may want to wrap it around another API that's idiomatic to Java. I said before, I don't think TensorFlow is the right target if you want to seriously do that. I think looking at the Onyx native libraries is much more interesting. If this gives a way out such that we may be able to start building more interesting and more maintainable machine learning systems in Java itself. I think Panama gives you that leg up, which we haven't had before. And I think will give that acceleration to developers to try this out. That's why I'm pretty excited. I think it can give that leg up. And with all the language features and other features that are coming to the platform, I think we've got a fantastic platform or means on which to explore this space and to really invigorate this space. It's been adopted by quite a few libraries and frameworks out there. It's hard to see what exactly this slide represents, but I'd just try and enumerate some of these. So because we were able to put this into a JDK as incubating in preview, it allowed developers to easily experiment with this API and give us feedback. So the Netty team experimented with the API and gave us feedback. The Lucene team did the same. They're all getting good results. What else is there? SSL support in Tomcat too. There is I/O libraries, I believe. There's JFuse, I think, which is kind of like an I/O library. There is another library called UCX that allows you to do RDMA communication. And there's a university in Dusseldorf that have wrapped that around in an idiomatic API to do the same thing in Java and get this very efficient net transport of memory via RDMA. And they can get pretty impressive results, very low latency round trip times in Java, comparable to native code. And I think that's very impressive. And they're able to do this a lot faster than if they were doing it using JNI, which gives them more time for the creative part. So wrapping up, we got two APIs. One is a safe, efficient way to access memory, which is a lot better than byte buffer. Doesn't have the constraints that byte buffer has. The memory segment that I showed you is actually a value-based object. All its fields are final. You can think of it as something that's immutable. When we get Valhalla, we can turn that into a value object, and then we start getting optimizations from C2 or the runtime compiler that allows more efficient allocation and management of those objects than we can get today. It also allows for deterministic deallocation, which you can't do with byte buffers. It allows you to manage your memory more. You can have pools of memory that you can reuse. It's up to you to decide what to do, depending on your requirements. And there's a layout description language, or API, that allows you to describe the contents of the memory, and then to describe how you do native calls, which leads on to the linker API, which allows you to dynamically link to native methods at runtime. And it copes with the different calling strategies of C on x86 or Windows. Now, the linker API isn't bound to C. Potentially, we could also link to other things if the opportunity arises, which have different calling conventions, and we can do that dynamically. It's 100% Java, no need to write native code. And together, they provide the foundations which JExtract builds upon to generate mechanical code for you so you can do the creative part. And foundation-wise, it builds on very key primitives in the platform that have been there for at least 10 years or more. And we hope that these APIs will be there for that long, and we can build primitives on top of those too. And we keep going like a tower. And so it's in preview in Java 20 today. You can look at Jet 434 if you want to do it. You can download Java 20 and try it out. But we're not stopping there. We're doing another turn of the crank, and there's already a new JEP out, and I recommend you read that JEP. The description in that JEP is excellent. You can download the JExtract tool for Java 20 and give it a try. And there's still more work to do here. We need to investigate how we can apply Panama to the JDK itself. So we use JNI in the JDK to call out to native methods. Don't like it, it's too much C code, it's hard to understand, bugs, security bugs are in there, and so forth. Maybe we can use Panama to bind to the zip API, zip.h, for example. There are other things, I/O libraries and so forth like that. There's some challenges to this, because as we use Java on Java, there's bootstrapping challenges, but we can overcome those, I think. This is going to make the JDK more efficient, safer, and easier to maintain. We want to integrate with the Vector API and SIMD so that we can pass vectors. There might be native methods that accept vectors as arguments, or vector registers, and we want to be able to call out to those. Java C2 generates stubs for certain intrinsics, like base 64 encoding or decoding. Those are effectively methods that, if we can encapsulate some of the calling conventions around what they do with vectorization in those things, maybe there's a way we can up-level more to Java. I'm just thinking off the top of my head here. But once this allows you to do other things that you couldn't do before, so it opens up new possibilities. I think there's more to think about with C++ support, which is more challenging. Often in C++, everything's in a header file and then gets inlined into your code, which means you have to curate and generate what code you want ahead of time. So that's a challenge. We are not complete yet with fully replacing JNI. We may investigate how to pass Java objects or Java arrays over. At the moment, we can't do that. So it's very, we can't say this int array is actually a pointer to an array of ints. It just so happens the native int array in Java just so happens to be compatible with the native C int array. And so you should be able to do a pointer to it, but it's not necessarily always the case. It doesn't have to be the case. For Hotspot has a great freedom to represent arrays in however it likes to way, although it'd be crazy to represent the int array any differently. But a Boolean array might be different. Okay. And that's the end of my presentation. Thank you. So you can rate it if you wish by going to that QR code and typing in JV11. Thank you so much.
We'll be starting in 10 minutes. We'll be starting in 5 minutes. We'll be starting in 1 minute. Introducing Aurelio Garcia-Ribeyro.
That's a lot of noise. Hello, good afternoon. So, good evening. Thank you for staying at the last session, and I'll try to get you to the happy hour, but hopefully you'll find something useful between now and then. So during this session, I'll give you a quick overview of Java Management Service, which we started offering in 2021. Now, a common question that I get when I talk about Java Management Service is, why would I need to manage Java runtimes? What's wrong if something is already running? Why do I want to update them? Just, it's running. Don't rock the boat. Well, there's a good reason why you like to update your Java runtime. A running Java application is the result of the collaboration between different components. You have the developer code, which is what everybody thinks of as the application, right? And rightly so, that's where all your business logic is, all that stuff that's unique to you. But developers, nobody writes everything now. You use some third-party libraries, and they'll be updated whenever the vendor wants to update them. And there is also the Java runtime itself, which at a high level is comprised, wait a minute, where's the, there we go, sorry. Which at a high level is comprised of the Java runtime and the JDK libraries. Now, the JDK libraries free developers from having to do a lot of common tasks, and they provide a unified base of features that all support, that will make Java work the same in all supported platforms. Now, the developer code and the third-party libraries are under the control of the Java developer. So they can only be updated if the Java developer updates the application. The Java runtime, on the other hand, is updated by somebody like Oracle and lets the users update their application without actually changing the developer code. Now, this separation between the developer code and the runtime opens the door for some interesting opportunities. Now, if you attended my earlier session, you saw a slide like this, where we showed that we're releasing a new version of Java every 6 months. That's pretty clear. But then some of them have a very long line of support, and others not so much. So the LTS releases get at least 8 years of support. The non-LTS releases every 6 months. But what does that mean? Well, after every release is launched, we produced critical patch updates for every quarter, and it will be receiving updates for its whole lifetime. Now, the number of updates that any release will receive depends on whether it's LTS or not. So long-term support releases will get updates, as you see here in this page, for many years. That's 11, 17, and 21. The non-long-term support releases, it's only for 6 months. Now, this page in java.com, release matrices, lets you see in a very graphical way what the others slide showed. Now, let's imagine that we are today running a program running on 17.06. That's the most recent version of JDK 17. Now, when the release, in April, as you can see, we have planned to release some critical patch updates for all supported releases. When that happens, Oracle being a contributor to open source, OpenJDK, we will put the source code for 20.01 in OpenJDK. And if there's any vulnerabilities that could apply to 17.06, then you probably want to patch that thing sooner rather than later, because somebody out there is going to start looking into, hey, what did they fix with 20.01, and could those fixes also impact 17.06? Well, you will, when that happens, you have two choices. You can update to the next version of 17. So we call that updating your runtime. Or you can upgrade to a different version, cross to a new release family. Either of those two would be fine, right? Now, there are many users out there that when they see this little diagram, they think, oh, I'm going to update only about the security vulnerabilities that Aurelio just mentioned, right? So we come up with a list of vulnerabilities fixed on every release, and you're thinking, That's why I need to update, right? You'll run some scan of your systems, and it will flag 1706 as being old, and you think, I need to update to avoid bad things happening to me. And that's true, and you should update for that. But let's also focus on the good things that happen when you update. It's not just to avoid bad things, right? So what's the good stuff that I get by applying these updates? So the real value is this one, right? Your programs work longer because you wrote them in Java. What do I mean with that? Well, remember those libraries that I mentioned? Those libraries get updated too. And what the libraries do get updated even in those releases. So most people think of the updates as a minor improvement in performance that maybe I can live without, right? It was working fine. But there's some improvements in the libraries that you really shouldn't live without. My favorite example is crypto algorithms. Now, here's some sample code. You're not supposed to try to understand it, but here's some sample code that could have been written in 2014, right, to securely read the content of https://java.com using, at the time, SSL v3, which was the common encryption used for HTTPS. Now, around January of 2015, we disabled SSL v3, and we said you should now be using TLS. So here's the new code that you have to write to use TLS 1.0 or TLS 1.1. Can anybody spot the differences there? Let me help you out by highlighting them in red. There's no difference. It's the exact same code. So your application, as written to use SSL v3, now is running TLS 1.0. And sure enough, April of 2021, we disabled TLS 1.0 and TLS 1.1, and guess what? Now you have to update your code to use TLS 1.3. And this is what I meant, right? Your program, written in 2014, before there was a TLS 1.3, is now running with modern encryption and can continue to work even though you didn't change one line of code, right? You didn't even have to recompile it. All you had to do was update the Java runtime. So this is one of the largest benefits of updating the Java runtimes. Now, what changes in these updates? Remember that I said you have two choices? Updates and upgrades. Well, with the updates within the same release family, we changed the minimum amount of stuff that is required to keep your application running. That includes those security vulnerability fixes, if there's any critical bug, time zone updates, some country changes when they do the daylight saving time, all of that that your program needs to continue having correctly, right? Sometimes the operating system changes something. If anybody here uses a Mac, they change their graphic engine so that instead of OpenSSL, they use Metal, and eventually they remove the old one, and will your program stop working? No, because you just keep updating your Java runtime, and Java takes care of that for you. As I said, we also disable some old encryption algorithms, we update root certificates, and we do some minor improvements. Now, the feature releases do all of that, plus new language features, new tools, some major changes to the JVM internals, and here's the catch. You cannot really move forward if you're carrying around an anchor, so you sometimes need to remove and deprecate old stuff that it's no longer as current. So we do take those out, and that makes then the choice a little different, right? Updating within the same release family, very low risk, right? It's going from 1706 to 1707 to 1708. You really shouldn't spend much time thinking about this one. You should just apply the patch. In the vast majority of cases, it'll just work. So my recommendation is we produce a CPU, critical patch update. I know somebody else uses those acronyms for something else, but what do you want? We do it on the third Tuesday of January, April, July, and October. You should try to apply those patches almost as soon as possible, on the same date. And only if it's mission critical, you should really bother testing first. For everybody else, try it out. And then if something blows up, you can always revert. Then I'd recommend take a look at the release notes. Chances are it's something simple, some change in some property, and you get it up and running again. If you do rollback, please do it only for the affected release. Don't do it for everybody. And it's not a license to just hold back forever. Figure out what's going on and update, because if you revert back, you're losing all of those updates. Upgrading to a different version, it's a little bit riskier. So I know some people want to do it all at the same time. My recommendation is do that when you're approaching the end of support of that version. So in 2022, we reached end of life of JDK 7. If you see that JDK 7 is approaching end of support and you intend to have your application running for longer, then it's probably a good time to move to a later version, right? Also, we do have some performance improvements that show up between releases. They don't impact every application, but if your application uses the new APIs or whatever, it might be worth updating. Sometimes there's a corporate mandate. Thou shalt use JDK 17 as of this date. You apply. And sometimes there's peer pressure. You don't want to come to the conferences and be the one raising your hand when people say, are you still using Java 8? Right. Now, another thing that's different because of this separation between the runtime and the application is how you distribute and update your applications. So if you're writing an application, say, in C and compiling it to a native application, you'll grab your code, you'll compile it. In this case, I'm using a Windows compiler, and you get a Windows program. It's ready to run. You can just distribute it to your Windows users, and everybody can use it. And they're happy with it, and they use it, and they don't need anything special to run it. Now, if there is a new change to your application, the only way for your users to grab the new version, even if all you did was recompile it with a new library, is you got to distribute it again, make it get to all of your users. So there's no update that doesn't involve you and pushing everything to the developers. Java applications are a little different. If you compile a Java application, you don't get native code. You get bytecode. Now, bytecode, in one sense, it seems it's a little harder to use because it doesn't really run anywhere. You need to have your user get a Java virtual machine, a Java runtime, for the platform on which they want to run. But so if you have a Windows user, they'll have to get the Java runtime for Windows from Oracle, and now they can make this run. Now, there's one benefit to this, which is the same bytecode can be run by people in other platforms as long as they can find the Java runtime for those platforms. So that's good. Now, if you update the application like you did before, say there's a new version of your application, you still need to redistribute it and push the bytecode. But, and here's where it gets interesting, you can also update the Java runtime. So imagine this application was running with 1706. Without you changing anything and redistributing it, if we produce a 1707, your users can update their application to use new libraries, to use new improvements, without involving the developer. The developer could be somewhere else, like drinking a daiquiri by now. So, in order to really get your value out of your Java, your investment in Java, you need to understand then, you need to get an always up-to-date list of every Java runtime installed in every one of your systems. And it'd be great if we can highlight the ones that should be updated or upgraded, because the other ones you probably don't want to be using. You always need a list of which applications are using each runtime, because one of the problems of having them separate is it is quite possible that you have a Java runtime that's not being used by anybody. I know I have been updated sometimes runtimes that I'm not using. Just, hey, there's a version of 11, I should update the next version of 11, without thinking, did I switch everything to 17? And I'm going to need a link between the two, right? Which one is using what? Now, using JMS, that's exactly what you will get, that complete list. Now, how do we do this? By relying on something called usage logging. which is available in the Oracle JDK. And here's how it works. If you look at the Oracle JDK, there's the description. You can turn on usage login, and it will create a local record with a lot of useful information. The ones that are interesting for our case is I have the date and time, the name of the machine, what was I running on that machine, and the runtime location and the version. If I look into a server nowadays, I will find perhaps one Java runtime. More commonly, now that we have multiple versions, I could have different runtimes. I could have some application running on JDK 8, another one in 11, some in 17. There's a handful there running JDK 20 as of today. Then I'm going to be able to perhaps, if I have a good scanner, find all of my bytecode. But then I need usage tracker to, every time I use one of those, create a record that matches them and tells me what's using what. Then I have an agent grab that local file, encrypt it, and send it securely to the JMS server. And now, once it's all nicely collated, I can create my reports about what's going on each one of those machines. Now, what I just described, who can use it? Any Java user running on Windows or Linux. This works on desktops and servers. And you can run it for workloads on Oracle Cloud Infrastructure, on some third-party cloud, or on-premise, so your own machines, wherever you're running them. You will need to get an Oracle Cloud account, because you're going to have to log in and see all of these reports somewhere. Now, when you get that Oracle Cloud account, Oracle will give you 10 gigabytes of always free storage. In most cases, if you're using basic discovery, that should be plenty. JMS will save the data for about 6 months, I believe, and you will not need more than that. So you shouldn't have to pay for anything. Now, if you have a very large fleet, you may have to pay for extra storage, at which point you run into the cost of OCI, which is just a few cents per gigabytes per month. So this shouldn't be costly. JMS per se doesn't cost. So it's only the underlying storage that you may have to pay for. Now, all of what I've described right now, those are the basic discovery features. And they're available to everybody. We also have some advanced features. The advanced features do require that you are a customer. And by a customer, I mean either you have a universal subscription or one of our legacy subscription products, or you're running an OCI. Now, if you are in those use cases, you get the advanced features. What are the advanced features? Well, once I have an agent in the system, and since we know everything about the JVM, we can discover not only what applications you're running, but what's going on inside the application while it runs. So let's look into some of the stuff that you could get using these advanced features. First thing, I could find a Java server. So the basic discovery will tell me I'm running Tomcat. But it wouldn't tell you much more than that. If you have advanced features, you could go and get, OK, inside Tomcat, what it's running, right? So you would not just get the list of Tomcat, Apache, or WebLogic. You will get, here's the versions that I'm running, and these are the applications running on those app servers. Another thing that you can get is we can figure out which Java libraries are being used by your application. So we can have JMS go and figure out, OK, this application is running. What libraries does it rely on? And it'll come up with a list, library 1, version X, library 2, version Y, et cetera, et cetera. Once we have that, we can compare those libraries and those versions against NIST database to figure out if there are known vulnerabilities in any of those libraries and flag them for you. And let you know, OK, your Java runtime may be current, but you're using this old library in one of your applications, and you should really upgrade that as well. This is what JMS would look like. We will sort them by how dangerous the vulnerability in the library is, and then you can go and update your application with the latest version of the Java library. Okay? Here's one of my favorite ones, too. Remember that example that I showed about how your Java library could change the protocol that is being used to connect? That was pretty good, right? It also means your developer has no idea what protocol is being used. If you were to ask the original developer, they would say, well, SSL v3. And then it just flips underneath them. And it has to do not only with what's on your server, but what's on the machine that you're connecting to. So it's sometimes hard to tell what the library is up to. But you know who knows that? The JVM does, right? When we're running, we know what we're loading. So imagine then, here's our little crypto roadmap. It's a public page, java.com crypto roadmap, where we tell you when we're going to do things like disabling some algorithm or adding a new one. Without JMS, you could go configure your runtime to future, disable now what we will disable in the future, try it out, see if it blows up, and if it does, you know that you need to fix something. Or you could use JMS to do it for you. So here, it's not only what we've done we're going to do in the future, it's also what we've done in the past. Here's the example of the disabling of TLS 1.0 and 1.1 that I mentioned before. Notice that this was disabled in 2021, as I said, in April. But if you look on the change log, right, at the bottom, you see that we announced it on October of 2019. So in theory, you had several months on which you could have gone and say, oh, look, I'm using TLS 1.0. I should update it. Or when I apply the update in April of next year, this thing is going to blow up on me. How do you do that now? You tell JMS to do it. So you can tell JMS, sample these applications so that I know which cryptographic algorithms are being used, and then compare the result of that with the published crypto roadmap. And the beauty of it is, I will compare it with the then current crypto roadmap. If you run this report 2 days from now, when a new entry comes up, something that was okay might now be flagged as problematic. Right? Without this, most people discover that they were using something when they apply the patch. It blows up. And then they have to go and configure and turn it back on or whatever. So this is one of my favorite features that I wanted to do for a while. We can then tell you something that not even your developer knew, right? In the same vein, anybody here attended the flight recording session with Michael Witzet? I really wanted to attend that one, but it was at the same time as my session, so couldn't do that. If you run Flight Recorder, how does it work now? You have to go physically to the machine, or you have to remote to each individual machine. You have to turn it on. You have to wait for the recording to be done. Then you have to either analyze it on that machine if you have mission control there, or you have to transfer it to some other machine and analyze it, right? And if you're looking at one machine or two, yeah, sure, no problem. But if you have a long fleet of machines and you want to do this, it's a bit of a pain. So using advanced features, I could ask JMS to turn on flight recording on any of the machines that I am managing for a particular application. It's not a blanket for everybody. You could say, in this application, turn it on. I want to record for, I don't know, 15 minutes. Once you have the sample, bring it up, get it out of that machine, and now it's in a centralized location. So it's a way of managing machines without having to go to each one of them and turn it on, right? The current incarnation of these allows you to specify how long of a recording, when do I start, and we have different sets of possible flight recorder events that you could choose from, so that, oh, sorry, I gotta verify an update here. Glad that it didn't show up there. So, so you can decide which level of detail you wanna record. Now, keep an eye, by the way, all of this extra information is more data. So remember when I said that basic usage was probably gonna fit in 10 gigabytes? If you go a little crazy and start turning these all over the place, you could suddenly go further out than 10 gigabytes, right? But all of the data is collected in your object storage. You could decide to move it somewhere else and then clean that up. Or you could pay a very low price and just keep it there if you prefer it that way. Finally, the basic features tell you whether or not you have Java installed, what's it, and which version needs to be updated. But you're still on your own, and you better have some sort of software that will allow you to update the Java runtime on all of those machines. Using JMS for the machines that are covered under the advanced features, you can ask it to install or remove versions of Java. So say you were in this example that I had before, you could go and say, okay, in all of these machines that are using 1706, first check to make sure that it's not just that they have it installed, but they're actually using it. And if so, install 1707 and remove 1706. Right? When you're doing the installation, there's an extra option, which is post-installation configurations. There's certain things that you can do that are preset. So it is common when you install a version of the JDK that it will overwrite previous settings, right? And you might want to give you an example, we're saying we plan to disable, we're not saying this right now, but in the future, we plan to disable TLS 1.3 in favor of some other algorithm. And we plan to do this in 2 years. You could say, yeah, I want that sooner. So you could tell JMS, install the version that is current today, and then go and disable this algorithm before Oracle does, because I want to get my systems at a higher level of scrutiny. So there's a set of pre-configured actions that will disable algorithms or increase key length sizes, or in the case of Linux, you can also tell it, rather than using the root certificates that come with the JDK, let me instead rely on the root certificates that come with the operating system, because that's, some people want that. So all of that could be done centrally from JMS for all of your managed instances. And here's what it looks like. You can select versions of the JDK. Before you delete it, you can see who's using it, and you can install new versions. You can install the current versions, which will be highlighted on the top. If you must, you can also install some older versions. You'll get a little warning saying, you probably shouldn't be using that one, but you got a good reason, go for it. So that's all that I have for you today on the existing JMS features. But that's not the end of the features for JMS. JMS is a cloud service. So it moves much faster than the JDK. So if you thought 6 months was pretty rapid, the next set of features of JMS is always, at most, a couple of months away. So before you have another one of these events, we will have added new capability to JMS. So we invite you to keep an eye on the JMS documentation. And if you want to try JMS, the easy way to do it is go to Live Labs. Okay, I gotta confess, the URL for Live Labs is really bad. But if you go to your search engine and type Oracle Live Labs, it's probably the top hit. And then in the search bar, if you type JMS, you'll get these 3 Live Labs. Perhaps by the time you do it, there will be 4 or 5. The first one, or actually I think it's the middle one of those, will handhold you through the whole process of creating your OCI account, configuring it correctly, downloading the agent if you're going to run it on-premise or in some third-party cloud, or turning it on, because if it's in OCI, you don't have to do that part. It's already into the images that are used by default. So give it a try. Now, if you're going to try the basic features, have at it. Anybody can do it. There's no restriction. If you want to try the advanced features, if you are a customer, again, have at it. If you're not a customer, the easy way to try it is run the workloads in OCI. Remember that I mentioned that OCI is already covered? So if you do not have any, if you're not a subscriber yet and don't have workloads in OCI, just take advantage of the 30 days, $300 credit that you get in OCI, put some trial workload in there, and you can try the advanced features there at no cost to you. If you are an OCI subscriber or are running in OCI, and you need extra help, more than you can get on these workshops, the support team is not there just to support problems in the Java runtime, they can also help you set it up. So reach out to them, and they'll help you configure agents and get it up and running. Now, I hope you go and try JMS, and let us know if you want any new features. As I said, we want feedback. We deliver these much more rapidly than any other feature in the JDK. And the usual, the final thing, remember that QR code, it's the same for every session. So if you want to rate this session, be sure to enter JV14 in the session ID in the survey. Thank you, and see you happy hour if you have questions.